Yeah, well, so welcome everyone to the Abstract Polkadot Hub module course. Kind of today we're not going to look deeply into code and into technical things, but rather we are going to show why Polkadot.js, which is the other library, not Polkadot API, but the legacy library that was being used in Polkadot. Well, it's still being used, but it's now being not super well maintained. And then we are going to show a small getting started with the library Polkadot API so that you are enabled already to start working on your assignment since this afternoon. We are going to show some developer tools that we built and are going to be very useful. And then we are going to explain late afternoon description of the assignment. So Joseph, your turn.
Okay.
You can cheer, Joseph. No. You can cheer. Yeah, thank you.
I guess I have to join a call or something, right? Ah, shit. Can I get like botón soy una cosa. Yeah. Sorry, one moment. Yeah. All right. Hold on a second. I need to join the call so that everyone can see me. I'm going to be honest with you. Today's session is not the most exciting session. But es aquí, ¿no?
Sí, sí, sí.
Hold on, I need to join. All right. Mute. And share screen, right? Okay. Oh, take off my camera. Yeah, I'm too ugly. Okay. All right. Moving on, like Donkey Kong. No, it's not it. Carlos did that. No. During class today. Why? Hold on a second. Give me a moment. This. Okay. All right. Cool. How are you, everyone? Good morning. Wake up. All right. So now we're going to, like, again, as I said, just a few things. Like, we're a small group, which is good. So please interrupt me, ask questions, raise your hand, like, insult me, whatever. We're here to have fun. So today's session is not the most exciting one. Like, what we're going to see is basically how we got to where we are at. So as some of you may know, Polkadot, the way it started and where it's going, it's kind of been a journey, right? Like, the core value proposition of Polkadot hasn't changed much, but how Polkadot does things and how it enabled dApps and whatnot has changed a great deal. So long story short, like, what you should get from this context, like, the too long didn't read, is that perhaps something that was designed even before Polkadot existed, maybe doesn't make a lot of sense to use it today, right? So yeah, this is more or less what we're going to be looking at, the context and why Polkadot.js didn't age well. This isn't, I'm not trying, like, I think it's very important to say that the goal of this is not to shame other people's work or to, trash other people's work or to whatever. Like, that's not it. We wouldn't be where we are at. Not that we're very far, but like, we wouldn't be where we're at with the Polkadot.js. But it's the goal of this is that you can understand why we need to move forward. So we're going to be using a little bit of we're going to be using Polkadot.js in contrast with modern tools. But the goal of many of the things that you'll be learning is precisely so that you can create other tools. It's not like to say, oh, the Polkadot API is like the ultimate like pinnacle of dApp development in Polkadot. No, it's more so that you understand how we do things. And quite honestly, if you want to do something similar with another language, or if you can get ideas on how to improve upon what we're doing, so that you can do it, that you can do it right? So yeah, without further ado, we're going to get started with this context. All right. So context, why PJS? You're going to be seeing PJS everywhere. PJS is Polkadot.js. And then just to make sure that everyone knows the difference between one and the other one, I'm going to refer as Polkadot API as PAPI because it's more catchy, and then people understand like, oh, PAPI, the new thing, Polkadot.js, the PJS, the old thing. Okay, so the Genesis story. It was a personal project that was started even before Polkadot existed, right? Like, what was the main? Like the guy that started Polkadot.js, like, read like the I think it was white paper, well, whatever, the Polkadot paper. And it's like, oh, this is really cool. And he started working on it even before Polkadot existed. So as you can imagine, when you start working on something that is very abstract, especially us software engineers, we love abstractions, right? And then you get abstractions and abstractions of abstractions and indirection, and this is going to, and things play really well in that imaginary world. But then when it comes down to actually, match with what came in reality, maybe it didn't go so well. So it started when only the specification was available. There was no real blockchain to interact with. There were no RPCs. There was no metadata, no nothing. So I don't even know what the code looked like back then, but it was based on anticipation and vision, whatever that means. Anyways, the first conversation, very cool. Like the guy that started this sent a message to Gavin Goods, like, look, I'm working on this. And Gavin Goods responded like, cool. Not sure how this fits in, but if it has a Polkadot ecosystem, so go on. So yeah. Okay, the result. The result was someone working like crazy. That is undeniable, and with a lot of passion. Also alone, into a library that grew organically within Polkadot. And basically, PJS is basically like the API, which is like kind of the library and stuff that you're going to see in a moment, and the Polkadot.js UI, which you will also see probably eventually, that it's around there. Something very important is that the JSON RPCs were created ad hoc, right? Like, since there was someone that was so passionate that had already started like creating like this library out of thin air a little bit, yeah? So that person was like, hey, I need an RPC for this. And then the runtime developer was like, all right, sure, well, here. And then that's how we got. Remember the shitty header? Anyone remember the shitty, the not so nice header that I showed you the other day in the example? Well, you can imagine how that happened now, right? Like, it's like, I need an RPC for this. And I mean, I'm not sure if that's exactly how it happened because I wasn't here, but like the Italians say, how is that? Like, se non vero ben trovato or something like that. Like, even if it's not exactly true, it's a good explanation for what we see now. Okay. But no, it is true. You'll see in a moment because we have witnesses from people that were there, and this actually it is true. The part of the JSON RPC is being created kind of ad hoc. Okay. Also, when Polkadot.js, when PJS was started, the protocol wasn't quite ready. Mostly the metadata didn't exist, right? So imagine having to create a library and having to have a way to manually create all the codecs for every possible chain interaction. And if you've seen the runtime of Polkadot, there are many chain interactions, right? So the guy had to be very, like the Jack, or like the creator, had to become very ingenious And he created something that is called the type registry, which was a pretty good idea back in the days. But because of the way, and I hopefully we're going to make an exercise in a few minutes that is going to hopefully help you understand this. This type registry that was created, it was a good ad hoc solution for what it came, but the problem is that it was not properly decoupled from everything else. So everything inside the Polkadot.js kind of libraries kind of impregnated this type registry concept. And then later on, when the ecosystem was at a point that it's like, oh, we don't need the type registry anymore because we have a newer version of the metadata that is self-descriptive, so we don't need all this madness. It was too late. It was everywhere, and there was pretty much no way to get rid of it. So yeah, this is a quote from Tomaka. Like, he's the creator of Smalltalk, the light client. He also was the lead of a project named Substrate Connect that sadly got abandoned, and maybe one day should be resumed because what he was doing is pretty cool. But he created a forum post explained that I highly recommend when you have time to read it. It's a little bit long, but it's very interesting. There is the new JSON RPC, it's in the forum post, and the name of the forum post is the new JSON RPC API mega question and answers. And in there, he stated, when Polkadot Substrate was first started, the set of JSON RPC functions was simply copy-pasted from Ethereum, given that the implementations already existed in the Parity Ethereum client. Then expanded in a cowboy way without being given proper thoughts. So he was there when that happened. I wasn't, but I take his word, and I'm pretty sure he wouldn't lie. But also, what we see in those, hopefully the examples that I showed you the other day should kind of match with this explanation, right? So what I'm trying to explain here is that Polkadot, basically, this library was created, was very tightly coupled to the Polkadot node, and that's never a good idea. I mean, perhaps it was a pragmatic solution at the time because it allowed them to kind of iterate quickly. But whenever you have, let me put it this way, right? In software engineering, there's a saying when you design systems. I don't know if there's a saying, but I say it, and I hope that you say it one day, which is good fences make good neighbors, right? You want to have good fences between your different systems with clearly defined KPIs so that you can be good neighbors. Otherwise, when there are no fences, it's unclear whether this is your responsibility or my responsibility, and then the systems become very tightly coupled, and systems that become very tightly coupled are very difficult to evolve. Does that make sense? So as we can see here, just the fact that the RPCs were created in a way that it was basically spoon-feeding a specific library is not great. Okay. So the other problem that we have is that Polkadot.js has a very monolithic architecture. And we're going to, right after this slide, I'm going to give you an exercise. I'm going to give you 30, 40 minutes for an exercise before we go to the break. That hopefully will, will illustrate this point quite a bit. So it has a very tightly coupled architecture. It has leaky APIs at all levels. I will explain what that means. It has a very convoluted JSON RPC provider. Remember that we showed the JSON RPC provider function, the interface for PAPI is kind of super that simple. It's you receive a callback function where I'm going to be giving you the message that I'm receiving, and in exchange, I give you back an interface with a send method and a disconnect method. That's it. If you call the disconnect method, I register this callback function that you've given me, and the send method stops working. It's that simple. The JSON RPC provider of Polkadot.js is, well, we'll see later, but it's insanely complex. Basically, it's leaking a lot of its internals, right? Like it leaks things like whether it has ongoing subscriptions, it leaks things whether it has ref counts, it's all over the place. And that makes these interfaces very difficult to interoperate, and it makes it very difficult to create providers for any kind of transport, right? This is a very big problem. We'll see it in detail later on in another session. But if you think about Polkadot.js, like it has like two main public APIs, right? One is the JSON RPC provider, which is basically what it allows Polkadot.js to be able to talk with a node, whether that node be small dot or WebSocket or a Tamagotchi, doesn't matter. But the other API, the other public API that is very critical is the API with a signer. Because as you can imagine, you want to be able to sign transactions with many different kinds of things, right? Like with Ledger, with an extension. So you need a good API for how you communicate with these signing devices, right? Ideally, this API, again, good fences make good neighbors, right? Like you will expect that this API is properly decoupled from Polkadot.js internals, right? Sadly, this is not the case, and it's not the case to this day, right? And my personal opinion, well, not only my personal opinion, it's other people's opinion too, is that this has been in great detriment to the capabilities and the evolution of Polkadot ecosystem as a whole, because it's very difficult to integrate, because we don't have, well, my team is actually working on a spec for a generic signer that is properly decoupled from the internals of any library, including ours. Yes, but
Is this the current issue with PJS, or is this just from the start they have leaky APIs?
from the start, it had leaky APIs from the start. But if there is one issue that has, had long-living consequences, if I have to say one that it's been a major issue, is most definitely this one. In fact, later we're going, I don't want to bore you now because I want you to get the exercise started as soon as possible, but later we'll examine, once we explain transactions, we'll examine like this ad hoc sign payload interface that it's used by all the Polkadot.js extensions. It's just like, okay, so imagine that you're the creator of a new library, whether PAPI or whether like Flashy, whatever you want. Like you want to create a new library, and you create like the perfect library, right? Like everything is beautiful, everything is well decoupled. But now all of a sudden, you need to interact with existing signers, right? Like, because, like people have installed Talisman, people have installed the Polkadot.js extension, people have installed Subwallet, and you need to interact with these things, right? Then you find out, it's like, oh, shoot, I need to talk Polkadot.js language now, right? Like, I need to translate my beautiful thingies into this way of how Polkadot.js wants me to send stuff, right? But not only that, is that now every time that we have a new important sign extension, for instance, remember that we explained not too long ago this sign extension that is like the check metadata hash? It's a sign extension that basically allows you to know whether this signing device is using the latest version of the metadata so that you don't get hacked. So when Chains started supporting the sign extension, every single dApp in Polkadot stopped working. Every single dApp. People were not able to sign transactions. And it's like, did Polkadot break? No. Polkadot was working fine. In fact, like this happened on Kusama, right? Like first it happened on Kusama before it happened in Polkadot, so it was not such a big deal. But it is a big deal, right? Like people couldn't sign transactions on Kusama. And the reason being that because of the leaky interface of sign payload, every single dApp had to upgrade to the latest version of Polkadot.js so that Polkadot.js could tell the sign payload, I'm not using this sign extension. It was not even for using the sign extension. It was for saying like, you know what? This dApp is still not ready. I'm still getting it ready. How sad is that? But this is because of the poor design of this, right? So even like, it was, what I'm trying to say is like, it was a shit show, right? Like, and that's nothing compared with the shit show that's coming with S3 and CP5, but that's for another moment. So like this is a time bomb, right? Basically, this is bad, right? Anyways, I'm spending too much time in this, like, but I just want you to understand that because of the way that it was designed, like we need to come up with better standards that allow for any library, any actor, anyone to build on top of Polkadot, and also with a good standards, we cannot have a truly interoperable ecosystem, right? Like if everyone needs to play by the rules of the leak abstraction of Polkadot.js, then everything needs to be kind of done on top of it, which is what happened for a long time, right? And anyways, so yeah, moving on. Yeah, I already mentioned this before, but like instead of, so when I mean by, sorry, I often use this term leaky APIs. Does everyone know what it means, a leaky API? Raise your hand if you know what it means. Does anyone know what it means, a leaky abstraction? You don't, okay. You do? Can you explain it to everyone? Because I'm tired. When, go again? Yeah, that's good. That's good. Yeah, another way to put it is that whenever you make an implementation, you must try to create an API that hides as much as possible the implementation details, right? So it's not always possible, but whenever possible, you should try to hide these implementation details from the public API. And why is that? Because if you accomplish that, you can make a refactor, a performance improvement, whatever, inside this implementation without affecting your consumer, without affecting who is using the API, right? So another way to, when I mean by leak abstraction, is what she said. Another way to put it is punching through different abstraction layers, right? Like whenever you have an abstraction and another abstraction, but the outcome abstraction leaks the implementations of all these abstraction here. It's kind of punching through abstraction layers. You don't have really good abstractions, basically, right? Like if you create an abstraction that forces the user to understand the inners of what is inside, that is a leaky abstraction, right? Anyway, so what I mean by leaky APIs is this, right? Like is APIs that do a poor job at hiding the inner logic of what is inside, right? So one of the things is like the type registry. If you think about it, right? Like the type registry was meant to be like this implementation detail that Polkadot.js was supposed to use as an internal workaround while the runtime didn't have the metadata, right? Like while the runtime was not being able to be self-descriptive, Polkadot.js had to come up with something, which was the type registry. However, this type registry, instead of staying isolated inside the internal implementation detail of Polkadot.js, which will have a lot to kind of get rid of it in favor of metadata, it started leaking everywhere. And then libraries that depended on Polkadot.js were also using it to create like their own encoders and decoders. And it was like this kind of virus that kind of spread everywhere. So then when metadata version 14 came, it's like, how do we get rid now of the type registry? Well, guess what? Polka.js never did get rid of it. In fact, what they did was kind of a workaround where kind of the metadata for teen generates the type registry, and then the type registry generates the codex. Like, this is a spoiler of what you're about to see, but it's a little bit insane. Anyways, and then the result of this monolith is a bit unfair, but it is true, is large bundle sizes, right? Like, large bundle sizes and horrible memory consumption. Like the performance of Polka.js is not great. A large bundle size per se doesn't have to be that bad, because you can do code splitting and whatnot. But if we really want to create decentralized applications, we should try as hard as we can that the footprint of the libraries that we provide for dApps should be as small as possible. So the long story short, I mean, this is a little bit unfair. Like no, it's not actually. So the main reason for the large bundle size on Polka.js is the fact that when it was created, there were certain common libraries that are very well audited and that are built in JavaScript that are for hashing and cryptography, like noble hashes and noble curves and whatnot. These libraries didn't exist. So for cryptography, it uses a WASM from Rust, basically the same WASM that it's used on the nodes. It's being used on Polka.js. But that wouldn't explain why today we still have large bundle sizes, because today Polka.js should have been able to kind of get rid of that and just use like the modern libraries. The reason why that hasn't happened is basically because of this monolithic design that has made it impossible for developers to completely get rid of that WASM, as you will see in a moment. So it produces large bundle sizes, and I won't get too much into it, but like, yeah, and it also produces a lot of waste in terms of memory consumption. Now, because I think it's boring to hear someone talking nonstop, and I want you to experiment the pains of Polka.js, I'm going to propose a simple exercise, okay? Now, pay attention if you are falling asleep. I don't blame you. If that's the case, I would too. But now it's time to pay attention, okay? Okay, so. What? Yeah, thanks. So here we have the docs of polka.com. And here, these docs, they do a somewhat meh job at explaining scale. But if we go down, we will see that it mentions a set of libraries that can be used for doing scale encoding and scale decoding, right? Yeah? You don't need to type anything now, just pay attention. I'm explaining the exercise. Once I explain the exercise, you can go bananas. So as we can see, it says like, hey, these are different scale codec libraries that you can use for playing with scale, right? There is one actually that's really good. It's called Scale TS. I'm going to show it to you in a moment. It has nothing to do with the fact that I built it. But one of them is, if you go to JavaScript, a lot of people who go to JavaScript, they find Polka.js API. So I guess I was lying. I guess that you can actually use Polka.js for modular things like doing just scale, right?
So this is just like a quick introduction on Polka API, just like 4 slides, and then it's going to be hands-on. So yeah, Polka API is like this library that we built, direction here. And this is a bit like our big selling point, right? So it's fully typed, but not only the library itself, which is built in TypeScript, but also it lets you generate the types for any kind of chain, as we have seen. Then we also support the light client, and not only that, but we take like extra care of making sure it works well with the light client, and we have been given like a lot of feedback to them. Then performant, lightweight, modular, yeah. So this is a bit the most important part of like these 4 slides, is a bit like the concepts, okay? So when we build a dApp and we want to connect with the chain, the way that Polkadot API works is we have this library here, and now you have to choose how you want to connect with your chain. So there are many possibilities, and we will go through them as we go to the model, but long story short, there's 2 groups. So you can either go the small dot way with the light clients, or you can just use a WebSocket provider, okay? So if you use a WebSocket provider, you connect with one of the RPCs that's already deployed in the chain. It's a full node, and there's like a public list that's published like in many places. But essentially, it's like, okay, I'm trusting that this node right here is going to give me the correct information, and if it's lying to me, then well, I'm fucked. That is nice, right? Or if that server gets a DDoS attack, then it brings my dApp down and so on. So it has this bit of trade-off. Or I can say like, oh no, I want to use a light client, and then I use another provider, which is called the SM provider from small.provider. And now your light client is running alongside your application. And the light client acts as just a new node, essentially. So it's not connected to one specific RPC server, but it's connected to the whole network, right? It connects to not every single boot node, but the thing is that to the light client, you give it a list of boot nodes, and then it connects to many of them and asks for other nodes that are in the network and connects to all of them. Is it working? No. No? Okay, yeah, sorry. So it connects to all of the nodes and starts requesting proofs and all of that. So that's trustless. A bit of the trade-off that we will see, especially in this setting, is that small dot is a bit slower, especially if the network condition is not good enough, because as it needs to request for data, it needs to get multiple proofs and whatnot, it needs to do more work. Then usually it's a bit slower, especially to start up, but then it's fast enough, right? But if your Wi-Fi connection that's in here, you see that it's not good enough, then you can just like switch to WebSocket provider. But like our recommendation is to always stick to the small dot one.
Essentially, today is an important session because you need to fully understand how the metadata helps us to accomplish what we want, and it's going to be very useful for the assignment as well. We will be doing a lot of hands-on, a lot of try to understand how to use metadata in general. So essentially, module 2, this is a mistake. Module 1 recap. Essentially, what is the runtime? Do you remember that Victor explained us that the runtime is the business logic of the chain? It has the state transition function and all that stuff. We would do a bit of recap. And why the metadata, basically, it's what it's most differential of Polkadot compared to other blockchains. And then we will do a big deep dive into metadata, which will take us the most part of the day. And then we will touch a bit on extrinsics, also known as transactions. We will not make much of a difference from extrinsics to transactions today. This will come in later days. Okay. So what's a runtime? Do you guys remember? It's the business logic of Polkadot-based networks, basically. Good morning. It includes the state transition function, so that piece of logic that helps us to go from one block to the next one, right? It also defines the algorithm needed, this state transition function, to determining the state in a deterministically manner. And it's important that it's part of the state. So the same state knows how to transition to the next state with the transactions that come from outside. Is that clear? That makes sense. We already know that from the first day. And yeah, essentially how we compare to other blockchains, right? For example, Ethereum, no? Or even Bitcoin is more is clearer. So how does Bitcoin go from one state to the next one? Well, it's not deterministic. It depends on the implementation of the host, right? There are some rules that need to be fulfilled, otherwise the other nodes will not be able to import your blocks. But you have a bit of, you can play a bit essentially, right? On how you include transactions that a part of the network might consider they are valid, but they would not include that into their blocks. You can include them, so we have a bit of play here. And in Polkadot, this does not happen. So that's very interesting. And the most important thing is that we can modify the state transition function. We can modify the runtime without modifying the host itself. So let's imagine that we want to transition from proof of stake to proof of work. Let's think about that. Ethereum did the other way around, right? Went from proof of work to proof of stake. They needed to modify their hosts. They needed to adjust essentially what was going on. In our case, depending on the change, we would need as well. But depending on the change, we don't need to do that. So we can do it with a regular runtime upgrade. Yeah, let's proceed. That's clear. Okay, what's the metadata? So essentially, it's the information we need. So the basic information we need to interact with the runtime from outside. So without being inside, without having the runtime, we don't need the runtime to interact with it, just with the metadata. It makes sense to us. Then basically it defines the shape of all the interactions. And so they don't tell us what the interactions do, actually. So the metadata does not tell us what is a specific transaction going to do. It just tells us the shape of it and the name of it, and also has some good docs. But the important thing is that we know how to execute that function, basically. So why is that? Let me check one thing, because I think I changed some of these things. Let me check one thing. Okay, yeah, it seems I just forgot to change the title. Yeah. Okay, yeah, I forgot to change the title. The current stable version is 16. Okay, but the rest is correct. Essentially, from last time we did this course, the stable version was 15. Now it's 16. There's not a big change, but some of the things are adjusted, and the information here is correct. So sorry for that. But yeah, essentially, this is the shape of the metadata. This is the thing that we get. Remember that what we actually get is a scale encoded blob, right? So a lot of bytes that we can decode into this known type that includes the lookup, all the types. You remember that Victor explained us that it's a normalized data structure. The types reference each other. Then we have the list of palette with all the interactions they have. For example, calls, storage queries, constants, runtime APIs, and also view functions. We will see them one by one. Then we have the extrinsic, which essentially tells us how to build a transaction. What are the things that we need to include into the payload of a transaction to be considered valid? Then the runtime APIs, which are separate from palettes, outer enums, and custom that we won't enter this one, because essentially this custom is just a field that the metadata developers left to the implementers to put whichever data they want. Essentially for us, it's opaque, let's say. It's just a bunch of bytes that we don't know what that means, except if we know the chain and we know what is coming. Makes sense? All of these terms should already sound familiar. Is that right? Yeah. Okay, so let's go one by one. The types. This is, so as I mentioned before, these are all the types that are going to appear in any network, in any part of the blockchain interaction. So if we have a runtime API that requires a specific input, it will be here. We know that everything is here. So this is the most important part and the part that we will interact the most when building a library like Polkadot API or anything like that. And as I said, the palettes, as you can remember from the first module, it's just an array of every palette that we have on chain. That not every palette needs to have all kinds of interactions, right? So a palette, a very structural palette that just helps to do some specific task in the background or whatever, maybe it does not need to have transactions, but it may need state. Or a palette that, I don't know, helps us to input some data into the blockchain, maybe into the block, maybe it does not need storage, maybe just with a transaction makes sense. So the important thing is that not everything is compulsory. Yeah. Is there a mic around? We didn't get the mics today, or yes? Ah, yeah, you got them.
Is it only the palettes that are being used, or is it every palette that's used inside of that blockchain?
So it's every palette that it's included into the runtime, right? So essentially, if the runtime developer created the runtime with 10 palettes, we will have the 10 palettes here. Even if they don't have any interaction, so even if they are palettes that are empty, so they only do background things that we don't interact with them, they are going to be there. Make sense? Okay. Then the extrinsic, as I said, essentially helps us to build a transaction. We will see that not every part of the extrinsic is present here. So there is a part that it's a known codec. So it's like this one. So in this codec, we know what's coming beforehand. So with extrinsic, it's a similar thing. Then APIs, and yeah. Okay, so let's deep dive into the lookup. Yeah, as we said, they define the lookup defines the shape of all types. And this is a small note that this is already scale info. What do I mean with this? In the set of crates that crates are basically like packages in Rust, right? So like npm packages, crates are the same for Rust. In the set of packages that Parity publicates, essentially scale info is the lowest level we go into. Scale info is a set of tools that help us to interact with scale, but they are already complex types. So remember that we explained that the primitive types are integers, booleans, and well, the compact, which is as well an integer. And then we have the structs, enums, and all that stuff. So scale info builds on top of this and gives us easy ways to essentially create our types. One thing is this lookup entry. So what does it include? First, it has an ID. Remember that this one is unique and is sequential. So the first type will have ID 0, next type will have ID 1, next type will have ID 2. Actually, since remember that there is no spec for the metadata. Remember that we said that in the first module? Technically, this sequential part, we don't know. But honestly, if they don't make it sequential, so essentially that they go, so 0, 1, 2, 3, 4, 5 until the end, every tooling in Polkadot will break. So that's why it's important, and why we always say we need specs and we need to have proper specs that explain the actual shape of the things. But yeah, anyways, let's consider it is sequential, and it helps us to differentiate from one to the other. So remember that we had, for example, the account ID 32, right? The address itself, it was ID 0, and inside that we had ID 1, which was an array, And inside of the array, which was ID 2, we had U8, right? So they reference one to each other. Then we had the path and type params and docs, which come from Rust. So essentially, the path is, as Victor explained the other day, it's where it's found in the basically the file system in the Rust project. Then we have all the Rust generics, which helps us to do some heuristics, but they are not really useful. And docs, yeah, if we want to read them, but they don't. So automatically, we cannot get anything from them. And then there's the use, right? So this is the most important thing. It's what it actually defines the type. And we will see one by one. So basically, we will see all the options that we can have here. Okay, let's see a bit of an example. Okay, so how is Zoom back there? Good. Yes. Metadata. Okay. Essentially, we have the JSON. We will leave the lookup for the end and the palettes as well. Okay. Remember that we said that runtime version 16 is the latest one. Here we have version 15, but I'm going to change network so we see one that is the latest. Essentially, version 16 was released maybe a couple months ago, or maybe 3, and it's not yet in all networks, right? So let me avoid that. Let's see. The good thing when you will see that we are using a lot this PAPI console. Remember that the address is dev.papi.how. This is going to be very useful for your development because you will basically be able to introspect a specific chain. And you will see that the first time it loads is super slow, but then we cache the metadata, so it will be faster in subsequent loads if I am able to find a node that answers me. I'm sorry, what? Yeah, because it's at localhost because I was testing a fix that was introduced by our beloved Giuseppe that it didn't seem to fix the problems that I have. But anyways, but I encountered others. So no, nothing. I just encountered others. I was testing fixes and stuff. So, but anyways, dev.papi.how should work perfectly. But yeah, why is that? Try with this one. But yeah, it's the same issues that you have when you don't find a good RPC. Same issues that I'm having at the moment. Okay, yeah, we found one that works. Okay, now we have version 16. That's cool. Okay, so you see that. Let's start with let's close everything. Okay, yeah, let's start with the custom, which is the easier one. You see that there is nothing. In most of chains, this is the case. So custom part will be empty because it's not being used, but it could be potentially used for example, a very specific parachain that, I don't know, does some kind of data ingestion or whatever. They could have here some kind of keys or whatever, but this is something that has to be known by the runtime developer and also by the dApp developer because we will not be able to decode it. We don't have codecs for this. Then outer enums, which is the next thing. Remember that we explained the other day, and it is very important, that they group up the interaction. So here we have the calls. So essentially in type 106, we have all the transactions that we have in the whole network, right? So they help us decode a transaction. Events, same. Events are emitted when we submit transactions. Events are emitted, we will see them afterwards. And errors, this is the same. So when we do a transaction that for any reason the transaction is valid, but it didn't accomplish the purpose it had, an error is thrown. Okay, next, APIs. You see that we will see them in detail more during the lesson, but essentially here you see that they give us all the methods. For example, inside core, we have version, we have execute block, we have initialize block. So essentially all the information is here. We have core, we have metadata, right? That returns the metadata at the runtime. So as you can see, everything is it's mostly descriptive, and even though it only defines the shape and the name, it already gives us a lot of information on basically what are we actually doing. Okay, next thing is the extrinsic, that we have the version, which is the type of the address in this chain, the call, the signature. So essentially helps us to decode an extrinsic. And then sign extensions, we will see them a bit inside the class. And essentially all the sign extensions we have on this chain. We have the list of pallets. For example, the pallet system, it has some storage, it has some calls, some events, and some constants, right? Okie dokie, let's continue and go one by one, understanding everything. Okay, let's proceed with the lookup, which we have up here. Remember that we saw some examples the other day, right? So we are looking at this part. We are looking at all the type where all the types are defined. Okay, so a type, the type definition can be all of these things, and we will go one by one understanding. First, we have the composite, which is a struct. In JavaScript we will call it an object, right? So it will be some key value pairs basically. So a hash map, whatever you call it in other languages. So which should be the easiest one. Then we have the enum, which actually is the most important one. It's the one that essentially allows us to have all of this recursivity, right? So one type that calls itself, for example, and with this enum, we can at some point break the circularity. Yeah. Then we have the two vectors. One is from variable length, a sequence, and the other one is from fixed length. For example, let's put an example. If we want to store a text, so if we want to represent a text in the metadata, we will say that a text is an array of letters, but it's going to be variable length, right? Because I can say hello and good morning, and these have different lengths. So it makes sense to have this separation. But for example, for a private key, public key, sorry, we know that the public key in ECDSA signing algorithm is 33 bytes. Does that make sense? So we don't need to have it variable length. We can go with fixed length. Remember that we explained that when encoded, we will not go super dive into scale today because we explained that already the other day. But remember that we explained that variable length encodes first the length of the array and then all the elements, and instead fixed length already encodes the elements because the length is already known by the consumer. Then we have a tuple, which is essentially the same as a composite but without names. So instead of being key value, so I don't know, foo, bar, bus, whatever, we have just index 0, 1, 2, 3. So usually that. Then we have primitive, which essentially are integers, booleans, and compact. And then we have this bit sequence that, yeah, it's not super used in blockchain, but in the Polkadot-based blockchains. But there are small use cases. We will not go into it today because the usage is very niche, let's say. Make sense? No doubts until here, I suppose? No. Then, which are the challenges of the lookup, right? The first challenge is this one. Type A that references type B and references type C, that itself references type A. So there's a circularity here. So when working with a lookup, you need to get rid of these circularities, right? And it's not easy and not always straightforward what to do with it. For example, in order to detect that there were circularities in the lookup, we use an algorithm that is called Tarjan strongly connected components. Anyways, if someone is interested in essentially graphs, they can look up here. And always our idea with the lookup is to be able to represent the whole type and its dependencies into one, what we call checksum. So essentially, in one identifier, we can compress all the information from the type itself and also the dependencies, right? That's why if we want to represent only the information of a specific type, we don't need anything of these cycles, or we don't care because we just take one element, hash it, and it should be done. But it's important to represent as well the dependencies. For example, one type that, for example, a struct that has only one element, which is a U8, so an integer of 1 byte, and another struct of one element that it's an integer of 128 bits, right? So it's 16 16 byte integer. If we only take the first element, they will look the same because they are, a struct of one element. But actually, if we go deep inside and look at the dependency graph, they are different because one it's one byte and the other one it's 16 bytes. Does that make sense? That's why we want to look at the dependencies, and we have to take into account the circularities. Yes? Okay. Then we have another type of circularity that it's more fine, let's say. It's easy to not take into account this one. And the mirror types, which I'm going to explain now, they are generated due to specifics of Rust. So actually, it's a bit of a leak of an it's a leak of the implementation in Rust of the runtime. Because what happens is, you have type A as before, that references type C, that references type B, and references type A, and it goes all the way around. But in one of the paths, so for example, this would be an enum, right? So A is an enum that can choose. You can choose between type C and type C prima, C and C prima. But if you look deep down into type C prima, actually it references B prima, that references A prima, that goes this way. And these two types are exactly the same. These two types are exactly the same, and these two types are exactly the same. The only thing is that we have this connection between them, so that actually type A and type A and A prima are not the same because A has this connection here. But if you encode them, they are the same, right? So we want to make sure that in our code, this is for the Polkadot API code, right? So not for a dApp code, but from the library perspective, we want to ensure that type B and type B prima are exactly the same. I'm going to say an example of this. For example, imagine that type, you see that here the problem is C and C prima, right? It's the one that connects the two parts. Imagine that type C is a tuple of two elements, which are B and B. So essentially a copy of B and B. And C prima is actually an array of fixed length 2 of type B prima. You see that they are actually the same. So one is a tuple and the other one is a fixed size array, but when you encode them, it's the same. You need 2 instances of type B. That's why it's important to notice these kind of things, and essentially take it into account when calculating your, basically when putting your lookup into a specific set of information inside your code. Does that make sense? You have something to that?
Yeah, I mean, this is very interesting, but like in which concrete scenario, like a library author will want to distinguish these things? Like what, when is this actually relevant?
So yeah, remember that we talked about compatibility, right? Um, remember that, for example, two chains might have super different types, but imagine a situation where we have a chain that updates itself, and instead of going from type C to, so instead of having this what we call an array of two elements, it goes to it updates, and now that specific interaction uses type A prima, because the type that it references is always a tuple of two elements. If we don't take into account this, we will say that, oh, no, this is incompatible, right? The two types are different. They are not the same. So we cannot treat them as equal. But if we take into account this, we would still say, yeah, actually the types are the same, and we can still be doing the interaction. Does that make sense? Do you remember what we explained in the compatibility section the other day? No? More or less? So essentially, remember what we said. We want to, let's take it this way. We said here that we want, oops. What? What is that? What? It's not going one by one. Wait a second. Okay.
Because that's like verticality. Now you have to go up.
Yeah, but I'm hitting space. Theoretically, it's, yeah, okay, here. Remember that all our idea is to compress one type and its dependencies into one checksum, so that we are able to compare types. Are these two types the same? They are the same if their checksum is exactly equivalent, okay? Then, what happens here? Imagine that we want to compare type A and type A prima. If we don't take into account the circularity, these two checksums will be will be completely different, right? Because type A only depends in one type, and type A prima depends in two types. So clearly, these two checksums have to be different, okay? So when we compare two interactions, for example, one that it's old and one that it's new, like old runtime and new runtime, we would say this interaction is incompatible, or at least only partially compatible, because clearly the old type had two children. Basically, it depends on two types, and the newest interaction, which is A prima, only has one. Does that make sense? But when we look deep into the type, if we take into account the shape on what is being encoded, which are the inputs and which is the output, we see that they are exactly the same, because type C and type C prima encode the same way. Does that make sense? Then we can flag this update from A to A prima as completely compatible. They are exactly the same. Is it better now? Yep.
So basically what you're saying is that the type that the triangle at the left will generate, right? Like if the unique identifier of that type will be exactly the same as the type that it will generate with a mirror type, yes?
Exactly.
Yeah, okay. So now I knew the answer, but like the thing that I want to reiterate, like Carla did a good job explaining, but it's a little bit it's a little bit mind blowing, is that we have created a library and we have created a system that anyone else can use, even if you don't use PAPI, like anyone can use for other things. That basically what it does is, given a runtime, right? we can identify for each interaction, regardless of how it's described in the metadata, because what comes in the metadata, like in the lookup, it's, as Carlo explained, it's an implementation detail of how the Rust code is generated. So we don't want to, since we don't want to rely too much in those implementation details, what we want to know is like which types it's this interaction yielding to the TypeScript developer. And it is important that it's to the TypeScript developer, right? Because basically what we want to know is like, is this interaction going to yield the same types across different chains, even if there is a runtime upgrade? Even like, a good example is like they did a refactor in XCM where they were like this mirror basically happened because they were creating a new set of types on XCM, and some types were exactly the same as in the previous version, and sometimes were different for the next version. But then there was like an enum that was pointing to one or the other, right? But for a whole subset, they were exactly the same. So we were able to detect that this yields the exact same types and also the exact same encoded data. So this serves us for two different purposes. One, for detecting compatibility across different interactions when there is an update. And the other one that it's more like niche maybe for us is we have this thing that we call the well-known types. So that when we generate the types, we have like these things that help you with the typings to like we have some well-known types for account ID, like multi-address and whatnot. And it allows us to basically detect if this variant is the exact same one that we have detected before. Anyways, like I don't want to hijack. I just want you to understand that why this is important. Like basically, like why we went to the trouble of basically being able to identify these things and to know if the types are 100% equivalent or not.
Yeah, so essentially our first implementation didn't include this. So didn't include this option that types can have this kind of circularities, but it was over a year ago that we discovered that this was the case with XCM, as Josep was saying, that is okay, the Zoom there, you can read, more or less. Is what was happening, right? So essentially the old type, or no, actually the new type used a fixed size array, so an array of 2 elements with this type inside, XCM v4 junction. And the old type was using a tuple, right? So XCM v3 was using a tuple of, this is a typo, XCM v4 and XCM v4, right? So if you look at them, yeah. So yeah, they are different, right? One is an array and the other one is a tuple. But if you look closely at it, it is exactly the same to have an array of 2 elements and to have a tuple of 2 elements, right? This is why you have to take all of them into account so that they actually are the same type to us. Maybe to another kind of programming language, maybe they are not equivalent. But in the case of TypeScript, they are. Because tuples and arrays, we use the same square brackets if you right? So this is essentially the example. And yeah, well, all the explanation is very interesting. So yeah, I will post this PR into the Discord so that in case anyone wants to read more about that, they can. I'm sorry? Someone already sent, huh? You guys are fast. I was doing it right now. Okay, so now it's clearer this. It's important to, so the important thing is that you understand that the lookup is not something that we take and everything is nice and it's a flower garden. No. So there are a lot of challenges. So what more challenges we have? The problem with second-class citizen, right? There are things that are critical to block. So, for example, an address. For example, money, tokens, amount, right? These kind of things actually are first-class citizens if you think of blockchain as a concept, right? But they are not in the metadata or they are not in our type structure. So for example, the balance is the amount for the account ID 32, which is the address, you know, this address that starts with 1F, blah, 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 blah. So the regular address in Polkadot, it's called account ID 32. We will refer always with this name. Actually, it's what I said, they are first-class citizens in the blockchains, but the metadata in the metadata are not first-class citizens. So actually identifying them as such is not trivial. Does that make sense? Let's see the example. Okay, first we go for account ID 32. We see this in the metadata. And actually it's always type 0, so the first thing you see when you open the metadata is that something is not properly done. So essentially we see this, SP core, crypto, so in the path we see SP core, crypto account ID 32. It looks like it's an account ID 32, right? At least they have it like that in their type system. We don't have type params. And what we have as a definition? It's a composite. What is a composite? You remember? Sorry? What is a composite? Okay, it's a struct. Okay, so it's like an object of things. And the first and unique item is of type 1. And what is it? 32, an array of 32 bytes and bytes, right? So an array of 32 bytes. So can you be 100% sure that this is referring to an address? Not really, right? Because it's an array of 32 bytes. This could be an address. This could be a hash, right? When you SHA-256, right? You hash it, 32 bytes. It could be that as well. It could be my PGP fingerprint of my, you know, that signing commits and all that stuff. My PGP fingerprint is also 32 bytes long. It could be that. So we have to do heuristics with the path to understand that this is an account ID 32. This is not our best. So basically, this is not what we have done to mark it as an address, but it's what it's done. So it's what we have to adapt to. We also think that we lost a very good opportunity of fixing these kind of things by essentially now I said that metadata v16 was released. So we lost a big opportunity here into changing these things into metadata v16 because who knows when next version will come. Actually, I don't think it will come soon because we almost have all that we need. So it's a pity. And then the balance is already worse. This is a balance in Polkadot. This is the amount of dot that you send to your grandma, right? So it's this type. It's a compact, okay, at least they tell us how is it encoded, of 128, so an integer of 128. This could be a compact or this could be my zip code, you know? So it can be my zip code, it can be an amount, it can be the, I don't know, the time elapsed since 1970, right? The UTC time, whatever. It can be whatever. So, for example, we cannot identify balances in our library. So balances are shown as any other integer. Make sense? Yep. Okay. Next problem, non-descriptive types. You remember that there was one guy when we were in the other module that asks, what happens if I have a type that it's three booleans, right? So true, false, true, false, true, false, right? So 3 booleans. Why do I have to use 3 bytes instead of compressing all of them into just 1 byte and using bits, right, to play? This is why not, because then types appear as non-descriptive. So some types, they create it in Rust so that, oh yeah, I'm super hacky runtime developer saving 1 byte per 1,000 used, you know, and it's like, oh yeah, you save 0.1% of the memory, yeah, you massive. But then when you see the metadata, it's like, yeah, now what I do with this, right? How do I interact with the network? Remember that the idea of the metadata is to interact with the network. So I need to understand what's going on, right? Let's see one example of that. Actually, 2 examples of that. This is the first one, identity data. I'm going to explain a bit, but essentially in Polkadot, I'm going to show an example of myself. Yeah, I will. Let me check. 1 second. Okay, copying an address that has an identity. Let's see in here. Let's go to people chain. There is a parachain that is called people, and essentially, it's this idea of identity, right? Let me show you in the storage that if I query for identity of, and myself, look, I just pasted here an address, and let's see what happens. You know, internet connection is slow. Our dApps works perfectly. I'm completely sure. Now the problem is that I connected with WebSocket, and our dApp uses small dot behind, so I was faster than the dApp itself. But whatever, let's query it. And what does it say? Okay, identity of this address. Who is this address, right? It seems that this address is reasonable. Not bad. Let's trust what it's here. So basically, some entity said that this address was reasonable. Okay, let's see who he is. Info. It seems like the name of this address is Carlo. Okay, looks familiar, you know. It seems that if you want to reach him on Matrix, you have to type to carlosala:matrix.org. Nice. There is an email here. Okay, so if an email is sent from this address, maybe I can think that they control this address, right? There is this PGP fingerprint. So if a commit is signed with this key, it's this guy. Then there is no image, fortunately, because images are big and we are in a blockchain, right? It has Twitter, GitHub, Discord. So this is something that we can do on Polkadot. We can identify, so an address can identify itself as, I claim I am this guy. And what this reasonable means is that some identity kind of try to, some identity that it's trusted by the whole blockchain says that it looks legit, okay? So how is this, this type info, so essentially one of these fields, every one of these fields, how does it look to the in the metadata? Let's see. Okay, we start from, let me change this, okay. We start from palette identity, types data, okay, the regular path. Okay, nice. Then it seems that it's an enum. An enum. We saw it's basically text, right? Every field. So why an enum and not a vector? But okay, let's see. Yeah, okay, because it can be none. So I can, for example, claim that this is my email, but I don't want to say which is my Discord account. Okay, makes sense. But then what is this row 0? And this, it's not moving, right? Okay, I have to. Yeah. What is this row 0? And this row 1? And yeah, there are a lot of rows, 17, 18, 19, 20, whatever, until 32. What does it mean, right? And then Blake 2 to 56. So it seems I can also input a hash here. So essentially what is going on is that instead of saying this is a vector of arbitrary length where you can input text, they said, no. Every length, we encode it as a fixed size array. So every one of these elements is, in this case, a fixed size array of 0 byte, a fixed size array of 1 byte, a fixed size array of 2 bytes, until 32. This is the worst ever, because something that if you had a vector, you could directly input your, I don't know, Carlos Sala there, and PAPI would understand that, compile that as a vector, and send it to the blockchain. In this case, you have to know which is this data structure, because how do you know that you have to use row 32 or whatever, right? So this is one of the non-descriptive types, which is horrible, and also made us build an SDK for identity, because for people it's not easy to fetch identities, because they need to, among other things, they need to work with these types that are not user-friendly. And even one more thing, look at this, look at this. There is none, and there is row 0. So this is a void, so this is nothing, and this is a tuple of 0 elements, which I don't know how do you encode a tuple of 0 elements, but these two things look the same to me. So even it doesn't make sense inside the sense of it. Yes?
But how did that happen? Basically, like why why I mean, who why did a runtime engineer do that to us, basically?
Okay, let's unveil that. It's his fault. I didn't want to move the board, but okay. If you guys at home can't read, you tell me. There's no black. Okay, let's try to encode manually this type. Let's say we want to encode letter A. So letter A is 1 byte. Yeah, exactly, 1 byte. Okay, so in our example, first of all, we have to encode the variant. Yes? So it's an enum, right? So the first byte will tell us which option to use from all of them. In this case, it has to be row 1 because it's 1 byte. And in this case, it's index 2. So, okay, the encoding of it would be 0x, then 02 because I choose option 2. At home, you can read. Not really, right? Well, whatever. You use option 2, and then we encode letter A. I have no idea which is the ASCII code for letter A, but A, right? Whichever this byte means. What happens if we had done it as with a regular vector? We had before, remember that there is none, so it's an option, right? So the first byte is, do I have this field or I have it empty? So we have it, right? So the first thing is 01 to indicate that yes, we have the type. Then, since it's a variable length array, we have to encode the length, right? Which is the length of our data? 1 byte, right? And 1 byte in compact, because remember that vectors are encoded in compact way, is 04, right? This means, okay, now you will find 1 byte afterwards. And then we have letter A. So, upper, we are using 1 byte, 2 bytes. And here, down here, we are using 1 byte, 2 bytes, 3 bytes. Amazing, you know. So these guys in the protocol in the other room, right? So they are super smart, right? They are the first in class in computer science, and they saved 1 byte. But what happens if, because normally we don't input A, right? Normally we have a name. So for example, my name is 1, 2, 3, 4, 5 letters, space 6, and then 4 more. 1, 2, 3, 4. It's not even a long name, so it's 10 bytes, right? It would save 1 byte out of 11 or 12. So it's like an 8% in memory. It's not that much. It's 1 byte, and we have to essentially, and this is it. We have to essentially use all of these shenanigans to understand what's going on, just because the guys in the other room try to save 1 byte. So you can hit them in the back when you see them, essentially. Giuseppe?
So could it be that they try to save 1 byte because in the old try structure, like the values were part of the proof and they were trying to save space in the proof?
Yes, but if you take into account the whole try and the amount of identities there are in the blockchain, it's a useless effort.
I agree. So yeah, what I was trying to point out, and this is something that we as app developers we need to start changing, is that there is a balance in everything, right? Like runtime developers, they tend to think of like, oh, what is the best thing that I can do? Like the most optimal thing that I can do for the WASM, for like the try and stuff. Like sometimes like shaving one byte and creating such a horrendous data structure that yields this kind of horrendous types that no one can make sense of, is that really worth it? The byte that you save in some instances, most definitely not, right? So it is always like for many years, like old libraries and like they were just like taking everything they did and putting any hack they had to put in place to kind of roll with that, but that doesn't scale, right? Like that creates a huge amount of technical debt. So the reason why I'm pointing that out is that it is about time that we start like pushing back, not pushing back, like just giving feedback upstream of what are the consequences of certain decisions, right? Like, so yeah, like in this case, it's a bit too late. Like that data structure is there for. There are other examples I'm sure Carlo will explain, and what it's done is done. But at least for new palettes, for like the new view functions, for it would be nice if we help them find the right balance between super duper amazing optimizations for the runtime versus how like everything is all trade-offs, right? Like you can have like something very optimal for the runtime, but if no one can use it, you know, how who cares, right? Anyways.
Okay, does that make sense? I see you guys a bit wasted. Let's do one more slide and then we take 5 minutes because I already told you that this was a, let's say, kind of strong lesson. So next one is next example, right? The voting. I think we already mentioned this in the other track. So in the other module. So essentially, the voting, right? Remember what we said. There are referenda in Polkadot, right? So that I ask you guys, hey, do you want to, I don't know, fire Giuseppe as teacher of this course? And then you guys can vote, right? Yes, no. And not only you can say yes or no, but also you can say, yeah, I want to fire him, but a lot. Like I want to really stake my tokens on it. So that's why you have this conviction that goes from 0 to 6. Essentially, if you choose a smaller conviction, you don't lock your tokens or don't lock them that long, but you have less voting power. And instead, if you choose 6, you have 6 times the voting power you should have by the amount of tokens, but you also have to lock your tokens. Does that make sense? And then what happens, right? A Boolean fits in 1 bit, right? It's yes or no, 0 or 1. Okay, then nice. Let's count bits. And then conviction, in how many bits does it fit? The number 6, it's 3 bits, right? Yes, no, yeah, yes, I assure you. So actually in 3 bits, you can fit up to number 7. So it can fit in 3 bits. So in total, we can fit these 2 numbers in 4 bits, right? Yes. So yeah, let's do a bit of magic. And we say that the vote, the yes or no, will be in bit, the rightmost bit. So the bit that, well, leftmost actually, the leftmost bit. So the bit that counts the most, right? The 8th bit in the byte. And conviction will be regular as in the least significant bits. Okay, and this is, everything looks very nice from when you think about that. Oh yeah, I saved 1 byte. I'm super smart. But when you see what does it yield, we have this type. Let's try to understand. It says palette conviction voting, vote. It looks like it's a vote, but yeah, it's heuristic in the end. Okay, let's see, no params. And what is the definition of it? It's a composite, okay, a struct. How many fields do we have? 1. What is this field? It's an integer. It's 1 byte. All of this magic, can you see all of this magic smashed here? Honestly, I know that it's there, but no one is telling me. So essentially, this is another problem And then in order to interact with it, you not only need the metadata, but also you need to go into Rust code to see what are they doing. Because in Polkadot, we have no documentation. So you have to go to Rust code. So essentially, these are two examples of how metadata is shitty due to, essentially due to implementation details of the runtime. Does that make sense? Okay. So what is the problem? Essentially, all the issues we saw, why are they? So essentially, because of the way the metadata is generated. So this kind of groups up all the issues we had. The problem with metadata is that runtime developers code the runtime, and there is a macro essentially that creates a runtime, and at the same time, outputs a blob of bytes. That is the metadata. And the runtime developer does not have control over what is there, or the only thing that they can control are the docs or these kind of things, but not the typing system like it is. This is bad and good at the same time, because normally runtime developers do not care about off-chain developers. So it's cool that we essentially it's auto-generated, and because if they would have to create the type system and all that stuff, they wouldn't do it. So this is good and bad at the same time. But the problem is that the generation system cannot be perfect, right? It could be better, hiding the implementation details, but it's not perfect. And this is essentially the issue. Okay. So here we finished with the part that is lookup, essentially. Now we are going to jump to the other parts of the metadata. Okay. So any questions around the lookup? No. Okay. 2B. What are outer enums? Actually, they don't need to be there. So it's just sugar. So we can essentially, we could create these outer enums from outside. These outer enums, what do they explain basically? They are like collections of all the transactions, all the events, and all the errors in the runtime. But you could build them yourself, right? Going through every palette and checking, these are all the calls, I get them. These are all the events, I get them. These are all the errors, I get them, right? So essentially, you could build them yourself, but it's cool that they are here so that it's a bit less work that we don't have to do. And essentially, this only takes 3 bytes, right? Because it's one type, which is a compact. Another type, it's a compact. Another type, it's a compact. It could be maybe 4 bytes, but 5 bytes, depending on which type it is in which number. But it's only a few bytes. And yeah, essentially that's it. These are not very important by themselves, but something we have to take into account. Okay, next thing. Runtime APIs. Do you remember that we talked the first day that we have the host, which is basically the node, the one that connects to other peers and all that stuff. And then we have the runtime, which is the one that executes the logic of the chain, of the blockchain itself. And they communicate themselves by, so the runtime asks information from the host through the host functions, and the host asks information from the runtime through the runtime APIs, right? These are the runtime APIs. And they do not only allow to the host to get information from the runtime, but also as users outside of the blockchain. For example, to do a dry run. Maybe we have a transaction. Let's take the same example as before. I logged my tokens. I have 10 dot, and I log them into whatever, voting, for example. And I want to send this 10 dot to Emiliano, for example. Can I do that? Well, if I go through the storage and check, yeah, I can see that I cannot. But what if I'm lazy and I don't want to know all the shenanigans of the chain? I can use a dry run. I try to execute this transaction. So basically, I send the bytes, essentially the bytes of the transaction I would like to submit to the blockchain, and ask the runtime, is this transaction valid? The runtime will answer, no, it is not, because you have the tokens logged and blah, blah, blah. So this is one cool thing that we can do with the runtime. The other thing is fee estimation. I have this transaction. I want to know how much it will cost to me. I send this to the runtime, and the runtime will tell me 35 dot. Yeah, I don't want to spend 35 dot. I don't submit the transaction. Yes.
Hey, Emiliano here. Is it always free, like the dry run?
Yeah. So the runtime APIs do not cost money because essentially, let's take it the other way. Let's imagine that we want to make them with a cost, so not cost free. Who would you be charging? Right? Because if I say, okay, I will create a transaction and tell the node, I am Emiliano, so I am this address, and I want to know if I can submit this transaction. And then the node takes the transaction and says, yeah, you can submit it, but now you owe me 0.1 dot because I executed this to you. And now Emiliano is 1.1 dot down. And then two options. If he notices it's me, it will break my legs. He will break my legs. And if he doesn't, he will be very upset because he lost 0.1 dot, right? So that's why we cannot make it cost.
So you can dry run in behalf of any person.
Exactly.
Okay.
How does it look? Let me show an example. PAPI console. Runtime calls, dry run call. So I would say, for example, let's see what happens, right? Sys, let's do balances, transfer from to, I don't know, transfer all to what do we have in the metadata, the runtime API's metadata? First, we have the name. In this case, in the case we saw, it's dry run API. So it's like the name of the namespace, right? It's like the name of the whole module. Then we have several methods inside every module, several or one, but it can be more than one. We have the name of one of them, which in our case would be dry run call. We will see more examples now. We have some inputs here. Sorry. Wow. It's so shitty. Okay. We have some inputs, like in this case, there were the origin, the call that I have to submit, and an integer down there. Then we have the output. So what will it answer? In our case, it answered the call was working well or was not working well. And then we have two small things that are deprecation info, that it's not very relevant, but basically it tells us if the Rust developer marked that specific interaction as deprecated. But this is new from metadata v16, and it's at the moment not being used that much, but it could be potentially beneficial, right? If we mark something as deprecated in the runtime, like in the next version, we will remove this code, for example. It's interesting because we, off-chain developers, we see, this will be removed. So maybe I find another path to accomplish the same thing, right? And then we have the documentation of it as in all the types. Yeah, so let's, but can you pass the mic? You already have it. Pass.
Sorry, yeah, right. This might be a little off topic, but I see the word API, so I'm interested. Is it technically possible for Polkadot or Polkadot's computer to be able to retrieve actual HTTPS requests just through traditional API calls to various, I don't know, API providers?
I mean, so the way we communicate with nodes is through these JSON RPC calls. There are JSON RPC calls that for their how they are built, they are not basically a lifelong subscription and all the stuff. Like this one, you can ask them as like as a one-off, right? Through HTTP. Yes, but normally what we do in PAPI, what you will find in the client is that you have a connection that it's already started, and essentially you can keep asking things. They will go through WebSocket or through Small which is not WebSocket. It's already there in your machine. But yeah, technically the API call, so the chain head v1 call, it can go through HTTP. It can go through any transport basically. The only thing is that it has to be JSON RPC.
Got it. So it's on the client's end, not the computer or the validators themselves, the people who then interact with the WebSocket, provide, I don't know, just like any kind of APIs
So
outside of.
the thing is that
outside of
WebSocket
blockchain.
is just a transport, right? It's just the transport layer. So we have to separate them, right? First, you have the transport layer. So where do these messages go? Essentially, how do they go from point A to point B?
Mhm.
This can be through WebSocket, but it can be through whatever, right? It can be also to the same local machine. It can be also with a pigeon, right? So imagine that Emiliano is my server. I go here with a paper, tell him, until it's JSON RPC compliant, there's no problem, right? The transport is not defined. I give him the paper, he reads the paper, yeah, it gives me an answer with another paper. It's JSON RPC, yes, he can understand the request, yes, I can understand the answer, yes. Until we find a suitable transport, there is no problem. So the transport layer is not specified anymore.
Right.
Does that make sense?
Yeah, that's
Nevertheless, with RPC with nodes, essentially, the full nodes that Parity produced, the most common thing is to do it through HTTP, through WebSocket, sorry. But you can do it as well through HTTP.
cool. Thanks.
Makes
Sorry,
sense?
it was a little irrelevant, but
Yeah,
I'm just interested.
it was a bit off topic, but yeah, it's important to understand. We will see tomorrow. You will have a almost as boring as today lesson about JSON RPC. So
We're
be
excited.
ready. You're ready. Sneak peek.
You're teasing us.
Some of it. Hopefully, I will not give that lecture because enough of boring lectures from me. So yeah, that makes sense, right? What I explained. Okay, so we have an example here. Yeah. First of all, we have the metadata namespace, right? So here we will have all runtime APIs relative to metadata. First one we find, metadata. You remember that we explained the first day. This will return, actually it tells us. It returns the metadata of a runtime. Okay, I can understand what this does. Which inputs does it take? Nothing. If you think about that, if I want the metadata, I don't have to give you any information, right? And the output is, whichever this means, which actually is bytes, a pile of bytes. And they tell us that it's not deprecated. Cool. Next one. We have the metadata versions, actually, because you remember that now we are on metadata v16. That metadata v15 is available. Metadata v14 is available because they are, essentially they are, so once you can generate metadata v16, you can strike things down and generate metadata v15. And once you have metadata v15, you can basically strap more things out and go to metadata v14. So actually, we can support different versions. And actually, this is the same. It takes no inputs and returns the supported metadata versions. This can be used. Where is that? This can be used to call metadata at version, so it already tells us. So with these versions, they are assuring, in the end, always the same. It's not assuring, it's just information that we get. But basically what it says is that for every metadata version that we find here, we can call a metadata version. And what is metadata at version? It's a runtime API that takes one input, the version, and this type is just a number, and it outputs. And actually, this type, you see that it's different than before because it's an option. What happens if I send here, the docs tell us, returns the metadata at a given version. If the given version isn't supported, this will return none. So if I ask for metadata version 75, the answer will be 0x00, so not found. And if I ask for metadata v15, the answer will be, because it's supported, it will be 0x01, telling, yes, I found it, and all the bytes. Let's see that in real life. Runtime calls, metadata. Yeah, we found them here. let's ask, which are the versions supported on this one? V14, V15, and this, that means unstable. Because it's U32 max, right? So if you remember, we already did that in what? We already did that in the other day, that if we do 32, what? Well, whatever. 2 to the power of 32 minus 1, it's this number, right? So it's the maximum number it can fit into these bytes. Okay, let's ask for metadata at version 75, right? Because, well, 73, it's the best number in the world, right? If you, at least if you watch Big Bang Theory, it is. And it says none, okay? And what if I ask for metadata version 15, that it exists? It says, yes, it exists, and I give you all of this. And actually, one nice thing is that, look at these first 4 bytes. Let's create a text encoder. And new text encoder. And let's encode I didn't prepare this, but it's interesting for you to know. From back, all of these first bytes, 0x6d, 0x65, 0x74, 0x, what's the last one? 61. Let's see what does it yield. No, it's the code, sorry. I'm sorry. Very bad. Text decoder. Text decode. Look what here. These first bytes actually are the word meta encoded. So that when we see a bunch of bytes, this is called a magic number. It's you might be familiar with it, I don't know, through other kinds of codec like, I don't know, MP3 or the Matroshka video or whatever. They have these magic numbers. So in the metadata, it's the same. The metadata always starts with this magic number, which is these 4 bytes, which decoded are the word meta. So if we find a bunch of bytes that starts with that, we can, so there's only one, essentially there's only one out of all of these possibilities that it's actually metadata. So it's already a good sign. Okay. Makes sense. Runtime APIs. Let's call some more of them. Let's see what do we have. For example, remember that we just do other examples. These session keys. This is a runtime APIs that different so the validators use, because blocks are generated with essentially blocks are signed by the validators saying that I produce this block, and these keys are hot, right? So they change every day basically, and the validators can use this method to generate their new session keys. So for example, we can provide the seed, let's not provide it, and if we what? Okay, they indeed have a problem. Okay, this is problematic. No, yeah, I understand. Wait a second, I'm in the wrong. I was in the wrong page because that is a parachain and session keys belong to the relay chain. So essentially, they don't have a problem yet. If we ask, I don't know, they actually have a problem. Well, actually, it should provide keys, but it's panicking. So we can tell the guys in the other room to fix this because it's important. essentially, this should provide a bunch of keys, one after the other. This is actually very bad. Yeah, this is really fucked up because basically no one can. Now I'm curious if in Polkadot it's happening the same. I'm sorry, what? Yeah, well, but Western and also Polkadot people. So I'm afraid it will be broken in Polkadot. Which was the one that was working for me before? Maybe this one. I mean, if it's fucked up in. Ooh. Not good. Yeah. Okay, session keys, generate session keys. We are now in Polkadot mainnet, and it's broken. So well, yeah, I think I'm not making a mistake. Well, whatever. This session key should return a bunch of keys that it's not returning, but as said, we are off-chain people. It's not our business. So, but yeah, there are many others like dry run, here we see. There are core ones essentially used by block producers to initialize a block, execute a block, all that stuff. And also an API to fetch the nonce of an account. Let's say, which is the nonce of myself, which is the nonce of myself. You see that now it already detected that it's someone known, and because it has an identity, it shows it. Okay, my nonce is 21, so I can only submit transactions with this number, whatever. There are all kinds of APIs that are useful for both node operators, block producers in general, and also for us users. Okay, okay. So let's proceed. Does that make sense? Yeah. Okay. Now, you want to share with
So if we look at the error, I think it's a little bit it's already telling us. I think this. So basically, like the key store is not linked, so it was not provided in the environment of the host function,
Yeah.
because this is a full node, and the generate session keys is meant for validators. So probably like the full node is not providing the host is not providing the host API for the WASM, because the full node is never expected to actually use this API.
It used to work actually.
Yeah, but it's very possible that the as long as you know what I'm saying? Like that's my guess. Like it has to be working, because otherwise, like basically the sessions wouldn't work, right? Like, and they are working. So I think if I have to make a guess, it's because also like if you notice like the crash that you get with small dot and the crash that you get with an RPC is different. Anyways, I think that's my guess. I think a validator will basically provide like the context that the runtime call needs, but a full node may not provide it because it's not expecting to use it. I think that's that. If I have to make a guess, I think that's what's happening.
It's likely to be that one. Yeah, for if anyone is curious. I'm sorry, what? Yeah, anyways, but people should be able to generate it as well, so it shouldn't be an issue. But yeah, whatever. Let's proceed. Okay, this is a long part. Palette metadata. As we said, all information in the runtime is essentially all the functionality is grouped in different palettes. So as we can see. here. Where was that? Here. What? Here. X-rays, yeah, for example. If we can see here, we have all of these palettes. So, for example, balances is one palette, identity is another palette, multi-sig is another palette, proxy is another palette, session, system. So, essentially, as you can see, the, transactions, storage, and all that stuff is it's put together by functionality, right? No, it's not. Besides that, we take all of this functionality and split it and show as well all the storage together, all the extrinsics together. But in terms of when you build the runtime, you have to separate them by groups of functionality. And what do these groups of functionality have? So first of all, they have a name, right? In this case, in our example, it's balances. Right? They have some constants, which are it is information that the runtime has that it does not change, or it can only change if you update the runtime. For example, if you want an example of this, it's how many, I don't know, how many eras are stored on chain. You remember that we talked about yesterday that staking information, it changes every era, basically. So on chain, it's stored, on chain, so the storage, the on-chain storage stores up to a number of eras. This number of eras, the amount, it's encoded as a constant, for example. It cannot change unless the runtime changes. We will see some examples of them. Then we have these two, event and error. What we said, when we do a transaction, events are emitted, which help us to understand what happened. You remember that balances system account killed when I try to do a transfer all, that is an event. Transfer, like the money moved from here to here, that is an event. All of those things are events. Then errors, that it's what happens when we try to do a transaction, that it looks valid. It's a transaction that can be included in a block, but it does not accomplish the purpose it has. For example, when I try to, I don't know, do system set code, it will tell me, no, bad proof. Not bad proof, bad origin. So you don't have the permission to do this. This is a type of error. And then the calls are all transactions together. You see that they are encoded as an option. Why is that? Because as I told you, not every palette includes events, not every palette includes errors, and not every palette includes calls. And for constants, you would say, why it's not an option? Oops. Why constants are not an option? Can someone guess? No. Actually, there can be zero. You can have zero constants. Because it's a vector, right? And a vector of length 0 is still a vector. Does that make sense? That's why we don't need an option. But in this case, since event, error, and calls are encoded this way, so basically they tell us, yeah, this is the type of an event. This will be an enum of all the possible events. This will be an enum of all the possible errors. Since we have it this way and not as an array, we need this option. And as always, as we find in all types, this deprecation info that tells us if a specific call is deprecated or not. Cool. Makes sense? Yeah. Then we have storage. What's storage? It's what we saw, right? It's this piece of information that goes all together with the blockchain, and essentially we can store things for later usage. For example, the nonce of an account, we can store them it's stored in the storage. We will see every type after the break. Then we have associated types. This is something that is new in metadata v16, that essentially it helps us to do more heuristics. We will see an example of that. But they explain us, so these associated types explain us which are the type names that Rust generics had when generated the runtime. We will see an example and it will be clearer. For example, let's go to, we will need some chain that has metadata v16 to see them. Have a crash. Metadata, okay. Let's look up at the JSON. For example, palette system. We close the storage, we close the calls, we close the event, we close the constants, we close the errors, and associated types. For example, this one tells us the nonce. This stores the number of previous transactions associated with a sender account. So basically, if we go to here, associated types, they show us which is the type of the nonce, which is the nonce is not an interaction, right? But it's an important type that we need to take into account. That's why they put it as here. And probably the most useful one is this number 3, hashing. The hashing system algorithm being used in the runtime. Example, Blake 2. There are chains that, you know that what is a block hash, right? You take the header and you hash it. But what does it mean to hash a header? I don't know. If it's Blake 2, then I have to apply Blake 2 and take 32 bytes. But what if it's a chain like Ethereum that uses SHA-3, also known as Ketchup, right? It's different. That's why they put us this type that if we go to type 553, it's of type void, but with the path, we can do the heuristics that we have been doing all day, and they tell us, yeah, it's Blake 2, 256, and then, okay, it makes sense. Let's look to another chain that has a different hashing mechanism. Western Bridge Hub, for example. There's this one that it seems to work fairly well. Okay, let's go to the JSON, palette system. We close all of this that doesn't help us. And associated types, hashing, 358. Okay, let's look up type 358. Oh, it's Blake 2. So Bridge Hub uses Blake 2. Now I'm embarrassed because I thought it used a different hashing system. So I don't know if there's another chain that sounds familiar. No, but whatever. Yeah, but Hyperbridge is not on metadata v16. Not even Polkadot is on metadata v16. So yeah. So essentially, if this would have been Ketchup, we would find here Ketchup 256. And then with these heuristics we have been doing all day, we can know, okay, let's use Ketchup instead of Blake 2, which is like the default for every chain. So as you can see, these associated types, they are not information per se that we can take in an automated way, but they help us to do this kind of heuristics. Does this make sense? This was recently included in metadata v16. Actually, it was something that we asked for, like we want to know which is the hashing mechanism for a chain, the hashing algorithm in the metadata. And instead of adding a field, that actually was, I don't know, instead of associated types, and this can be whatever you want, because as you can see, there is a name, there is a type, and there is some documentation. So this can be whatever you want. Instead, we would have preferred an outcome that would be, I don't know, relevant stuff, or whatever name you want. And inside that you have hasher, and you know that you will find the hasher there. Or whatever, nonce, and you will find the nonce, so a properly specified thing. But this is the closest we could get, and at least now with some heuristics we can guess. Make sense? This is not super relevant, and this is only useful for low-level library builders, but it's okay that it's here. And we have view functions. What are view functions? There is an idea now. So basically, a decision has been made to move a lot of logic from this is an internal job. Sorry. Basically, yeah, what I was saying, a decision has been made to move a lot of logic inside of the inside of the runtime. For example, you remember this voting type that was super shitty, that actually was vote and conviction, and they compressed it all in one byte? So the idea of these view functions is that there could exist a view function inside of the voting palette that says, convert shitty byte compressed into something that I can understand, like voting and conviction. So this kind of logic, they want to abstract it into view functions. Actually, the view functions are very similar to the runtime APIs, but specific for palettes. And we can see an example of that. Not a lot of palettes use them yet, because this is also new from, this is also fairly new from metadata v16, so they are still implementing them. But if I go to, they are that new that we don't even have them as a like first-class citizen in our console, in our dev tools, because since I think only 2 palettes implemented them, it doesn't make much sense yet. Okay, let's look. It's in Proxy Palette, for example. Proxy Palette has them. Proxy. Here, Proxy. Okay. View functions. For example, we have these check permission view functions. There is an ID, so that this has to be provided to the blockchain so that it knows which view function I want to call, because they are called in a bit of a shady way. But anyways, it's not relevant. And it says check permissions. You know what a proxy is? I think we put this example at some point in the past. Basically, is me, I am Carlo, and I trust that Victor is basically my colleague, and if he does not behave well, I can kill him directly. So I will let him have permissions over my account, because I don't know, maybe I want him to pay some bills for me because I'm out of office or whatever. So I delegate, I say, okay, so now the account of Victor can sign on my behalf, right? So essentially this view function, what does is, if you provide a call and you provide a proxy type, so because not every proxy is equal, right? I can, for example, give Victor permission on my staking calls. So basically he can change my nominators and all that stuff, but I don't want him to transfer money from my account. So essentially what this call does is it takes a call, so a transaction, and it takes a proxy type. So for example, type non-transfer, which is a type that allows to do every call except for transferring money. And this will answer yes or no. So is this essentially, does this proxy has permission or has not to execute this kind of account? You know, you see that this is logic that is intrinsically part of the runtime, right? So it cannot be exposed in the metadata in any way, because it would be difficult, right? In that way, we have this kind of view functions to help us understand basically parts of the algorithm of the state transition function that cannot be exposed in any other way. Or for example, is superset from the same idea. So essentially, I have 2 types of proxy. For example, any, which can execute any call. So basically, I give Victor full power on me, like I would give to my attorney, for example, or whatever. And I want to check it against non-transfer, which gives power over all calls except for transfer ones. Actually, it will answer yes, because any is a superset, so it takes all accounts, all calls that non-transfer has and other ones. So as you can see, other different kind of logic that it's inside the runtime, but it's good to have it out here. And now I'm going to take one question if someone has. Yeah, and then we do this important break. And I promise future lectures will be more engaging. So,
Adrian here. I was just wondering, it's really loud. Is the proxy stuff, is that a palette for delegating who is the proxy to?
Exactly.
Okay.
So there is, as I said, we group functionality in Polkadot by, so we group different interactions by functionality. In this case, the proxy palette is, its only purpose is to delegate power on another account. And there are different things to do this, but in the base, there's always delegating, so letting other accounts do things on my behalf. We will spend the next hour talking about storage, okay? How we see storage from the off-chain perspective, so from the metadata perspective, okay? The other guys in the protocol track, they see how to actually create storage entries and all that stuff, but we need to know how to use them from outside. Okay, so this is the shape the storage information has on in the metadata. So first of all, we have the prefix, as always. We always have the name of the palette here. Then we have a name for every entry, because we can have multiple ones per palette. I don't know. Balances, well, system account and system block hash, for example. There are two different entries inside one palette. Then we have this that Victor already mentioned, I think it was yesterday, that some storage entries are simply optional, so they can or cannot be. So if you go to look for a storage entry and it's not there, it will just say none, I didn't find it. Or the other type of storage entries are the default storage entries, so that if you don't find it, the supposed value, the value that you are supposed to use is the one that is written here in the default. Okay? For example, this is the case for accounts, right? When we ask for the balance of an account in the storage, we see that it's 0. So 0 in this case, it's the default value for the account. Does that make sense? Okay. And then the type, this is where this is like the most difficult part. So let's try to go step by step. This is the actual kind of storage entry we have. We have two kinds of storage entries. We have plain ones that are accounts that do not take any input. So are storage entries that do not take any input. For example, I don't know. What's that? I ran out of ideas. What's that? Let's see an example. Like block weight, for example, yeah. System block weight, it tells us how big the block is, the last block was, for example. And these are the plain ones. So these ones that just tell us, okay, it takes no inputs, and the value inside is of this type. This type would be a reference to one of our lookup types. You remember that we talked before? So it will tell us you have to go to that lookup type in order to decode. And then we can have a map, which is the interesting thing. Because, for example, system account, it's one storage entry, but has an input. So it has things underlying there, right? So in this case, the key in this case of the account would be of type an address, and the value would be whatever is the value of the storage entry. And then we have this thing called hashers that essentially is what help us creating the key, right? Because the key is not all the things concatenated, and it can be, but generally it is not. We will see examples with afterwards with the PAPI console, but essentially they tell us how to order all of this data, all of this information, the prefix, the name, and the mapping here. So the inputs that the storage entry takes in order to create the final key, right? For example, let's see an example. System, extrinsic count. This is an example of a plain one, right? So let's read the docs. What is system extrinsic count? The total extrinsic count for the current block. So how many transactions were there? They tell us it's not deprecated, as always. And we see that it's of type plain. because it does not take any arguments. It's just the number of extrinsics. And the type is type 4, which is an integer. So how many extrinsic were in the last block? Let's try to run it. Extrinsic count, as you can see, it does not show me any input. And it tells me there was 0 because Western is super used these days, as you can see. Then what else? But you see that we already encoded a big key, right? What is all of this? Actually, the key is only the name, so the prefix and the name of the storage key. So actually, system account, right? Extrinsic count, sorry. They are kind of like encoded in a special way, but that does not matter. We handle that from below, but essentially there is a way to, so essentially I can transcribe this to system and extrinsic count. And then we have another example, which is account. Exactly. They say it's of type map. The key is 0, as we saw the whole day. The type 0 is the account ID 32, it's the address, and of value 3. Let's check it out in the console. What's that? So we go to metadata, room, palettes, system, and in storage we select account. They say the key is an account ID 32, and the value, the type of the value itself, is an account info. And what does an account info is? So essentially just the nonce of the account, consumers and providers. This is something internal, essentially. We don't want to, we don't need to track that. And sufficiency, it's also the same. And data, which is actually what we are looking for. The amount of tokens that are free, so that we can use, we can send, etc. The amount of tokens that are reserved and frozen, which are the ones like when we stake, right? That we cannot send those tokens, but still they belong to our address. These are here. And also the logs when we vote, right? You will see that there are two types of logs, frozen and reserved. And you can think about why there are two types of logs. Think about that. Think about the difference between locking for voting and locking for staking. We will unveil that at some point. Okay. Yeah, and if we see the, okay, it says the key is Blake 2. So the type of the key, let's say the hasher, this is the hasher. It's of Blake 2, 128 bits, concat. What does this mean? It means that the key is built of two things. First of all, the prefix and the name, so system account, and then we take the key, which is our address, and hash it using Blake 2, only the first 16 bits, and also we concat our key. Why do we concat? So why we hash and then concat? That doesn't make much sense, right? It's like, or you put the key or you concat. Well, the thing is that since, imagine that you find a storage key that it says, you can decode the first part, system, account, and then you find a hash. You know that hashes are secure and it's a one-way function. So you can hash things, but you cannot unhash things. So that's why we add the concat, because we want to be able to decode an actual key. So when we see a storage key, we want to see which is the key that produced that one. Does that make sense? Yeah, it's a bit it's a bit complex. Let's think one more time. Where is this? Okay. Essentially, wait a second. Let me open a console. You have not seen it. Wait a second. Let me open a console. Okay. Which are the hashers we have? Then these are all the hashers we have. The first one is identity. So essentially taking the key as it is, encoded in scale, and append it on top of system account. Okay. Then we have 2x64, which is, this is another hash different than Blake 2. It's a non-secure hash, so it does not prevent unhashing basically. And then we have Blake 2 concat. But also we have this option, which is Blake 2 128 and Blake 2 256. These options, we believe, should not be used unless the key is super long, because they do not allow. So essentially, you saw that we see the full key here, right? Account or me. We see the full key here, right? If we are using one of these concat hashers, we are able to find, actually I can find my private key, my public key. Let me show you. Let me show you. Is there a, oh, there is not. I'm going to use subscan, it's going to be faster. Okay, let me copy my public key. If I, here, you see that this is the whole key, right? If I look for my address, and I remove the 0x properly, we see that I find it at the end, right? So I can actually decode this key and get both the name of the palette, the storage entry we are targeting, and as well the arguments. But if this, if the hasher, instead of being Blake 128 concat would have been Blake 128 directly, what we would find that the storage key would be all of it except for my address at the end. And this you say, oh, it's a shorter key, maybe we want to use it. But which is the issue with that? That if I take this key, since my address is hashed, I am not able to go back to my address. So the key acts as an opaque token. I don't know what does it mean. For some, so in general, the only moment this is useful is when keys are actually very, very long. So when there are a lot of things, they might have a point, the protocol guy saying that, yeah, but we don't want keys to be that long. But in the normal cases, in almost every case, we will find concat keys. So in the storage, there is always this, the identity, essentially the plain text key appended on top of that. Does that make sense a bit more? With the example? What about that? More or less? The thing is that, so when interacting with storage, always, this complexity is handled from inside of PAPI, right? We have all these libraries that essentially see, so check which is the hasher we find, and we know what to do. But it's important for you to understand that sometimes there are storage entries that when you do the get entries, have you tried doing some storage with Polkadot API, right? You can do, I don't know, system account, get entries. Don't try that because you will never answer, it's too big. But anyways, for other ones, get entries and you get all of them at once, okay? And they tell us, okay, this one has this key. So there is this key and with this value, this key with this value, this key with this value. There are some of them that since they use one of these hashers, we are only able to say, okay, this is the hash of the key. We don't know which is the original key that produced it, but this is all we can give you. And if they use one of these three hashers, we are able to find the keys, essentially. That's why we prefer way more these ones, because they yield more information to the off-chain, essentially, when you are building a dApp. Does that make sense? So for instance, I don't remember which was the name of okay. Okay. Core time provider, core descriptor. Let's go to see an example that one that does not use concat. It's in the core time chain. What's the name? Provider, core descriptor. What? They removed this entry. Well, it seems they removed this entry. Is that? Do you know, Josep, if they removed this entry? This entry, this is the only example we found from with a hasher that is not concat.
Oh, you are in the core time chain.
Yeah.
Look at the relation, I mean.
Yeah, I mean to the relation.
Huh?
I mean the I mean concat.
No, but I'm checking the relation because I think there's a reference. Even if check one more. I could be wrong, but I don't think they have a rule.
Yeah, I don't remember. Well, essentially, what I'm trying to tell you is that most of the storage entries use the concat hasher, so we don't have this problem. We can always, from both sides, so both when sending, essentially when creating the key, we can hash it, and when receiving the key, we can decode. What's going on?
Go to Western Relates block. Go hard refresh.
Western.
Go to Western Relates. It should definitely be there.
Yeah, it's in, okay, it's in the relay chain. For descriptors, yeah. You see that this, it's small again. You see that this one hashes U32 as with two, so essentially this hash. So if I say 0, if I say 0, the end, look, it ends with 6, 8, 4, blah, blah, blah. If I change to 1, it changed to 15A, 8B, I don't know. So things that I cannot understand, basically. They are not an integer. They are a hash of an integer. So if I check which are the keys that in my tree of storage, I'm going to look for all the keys that exist there. When I check them, actually, I see, okay, this key has a value, but I have no idea what that value, what that key means. And this was most likely a mistake from the person that implemented this palette, because there is no point on hiding the key. So that's why if you at some point find a key that essentially you cannot decode, this is a good point to again, open an issue to them and tell them, well, this is shit. I cannot work with that. And actually for you, it's also bad because you are not able to introspect what's going on in your chain. So, but yeah, imagine a situation when the key might take, I don't know, an arbitrary number of bytes, right? The key might be, I don't know, 300, 400, 500 bytes long. In that case, it might make sense to use this kind of hashers. And if you want to know what that key means, you can always use an indexer to see when that changed and essentially find the transaction that changed it. But anyways, it's the only point it makes sense. Make sense? Yeah? Okay, let's do some storage queries. For example, one that you will find often doing, it will be staking and nominators, right? So let's see. Let's go to Polkadot. Which one was working? And this one was working. Let me copy a wallet that has staking. Okay. Okay. I have Giuseppe's account here that has staking. Yeah, there it is. You are not staking? Oh, shit. I already prepared this account. Okay, so whatever. Let's check. We have an issue around that. Let's check nomination pool then. Shit, it's try to check this issue. It's
Probably that you were out of
It's about like everything is changed. It has nothing to do with what.
but it's empty. So it has only a no. It has there is only the RPC. So here there's only an RPC and a chain. No need to change RPC, but whatever. Okay, nomination pools, for example. Whatever. For example, we can check which is the minimum bond required to create a pool. This is the amount that the depositor must put, blah, 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 query, and it tells to create the minimum value to create a nomination pool, it's 500 dot in that case, because it has 10 decimals, if I'm not mistaken. Yeah, these are 10 decimals. So 500 dot. Another one would be system account. So let's check the information for myself. I have loans 21. I have this amount of money free. This amount of money is reserved because it's for staking. I have no frozen amount, and these flags that are not relevant to us. Yeah, then I don't know, balances locks for example, for myself. Not locks, holds maybe. Or it was freezes. Yeah, it's holds. Yeah, it says that my account has one hold, which is in the delegated staking, so essentially the nomination pools. I have holded this amount of whatever that means. The important thing is, were you able to access the storage through the API? So through the API.query. Blah 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 blah. You see there, it's very easy and it's already fully typed. So that's the important thing you have to understand. Any questions until here? No? Okay, let's proceed then. This, as said before, this is not extremely relevant when you are working every day, essentially, because most of the time, as it is on every coding anything in the end, if the abstractions are properly made, you don't have to worry about all of these details behind. You can work directly with a clean API like the one we provide or others, if there are, and just focus on what you are building and not how. But it's important for us that you understand how all the background of it works, so that then when you encounter, I don't know, imagine that you are doing storage and you encounter one key that cannot be decoded, right? That it gives you directly a hash. Then you would see, I'm not expecting this. But actually now you understand that it's because of the implementation below that essentially we cannot give you the key. But yeah. So then let's start with extrinsics. Then it's, yeah, okay, let's start. It's half before. Okay. Oh, sorry. Okay. What is an extrinsic? Essentially, this is going to cover probably this half an hour and then a bit more on the afternoon. Essentially, we're going to understand what is extrinsic, what is a call, what is a transaction, so all of that. Then we will deep dive into the extrinsic before, which is the one that we use currently to submit transactions. But there is a new extrinsic B5 that I say it's future, but actually it's present. You can already submit extrinsic B5 in Polkadot, Kusama, or any other chain that it's fairly modern, but it's still not usable. So that's why I call it future, but we will kind of understand them as well. So first of all, what is an extrinsic? Actually, this is like a definition. An extrinsic is a request to the runtime to modify the state from outside of it. So essentially, if we do not submit transactions, the runtime will keep producing. The blocks will be produced the same way, even if there are no transactions. And it will just, the state transition function will go from one state to the next one, but just with the default thing, right? So all of these hooks that we talked before, like initialization, finalization, they will be run for every block, but we don't have any changes to the transaction by an outside actor like us in this case. So essentially, this is the idea. So that's why it's called extrinsic. In Latin, X means like from outside, and intrinsic would mean from inside, right? So that's why it's called extrinsic. And until the day after tomorrow, extrinsic equals transaction. We use both words to refer to the same thing. So something that the user sends to the network. Yeah. Thomas, can you pass by the? You don't have that.
What if there's like a chain reaction, like one runtime triggers, or one smart contract, whatever, triggers a call into the smart contract? Are those still extrinsics along the way, or is it just the first extrinsic is like what starts the initial chain?
If we are talking smart contracts, smart contracts cannot activate essentially themselves. So they cannot have like at block 2 million, I will do something. You cannot do this. So if it's a smart contract, it needs to, someone from outside essentially needs to pay for the fees.
Yeah.
But regarding if it's not a smart contract, it's what I said. So the runtime does some things on its own without the user, without anyone from outside doing anything. But with regarding changes that are not automatic, you need to pay fees for those things to happen. And the way to pay fees, so to make the chain do something you want, it's through an extrinsic.
Okay, so it's like the first initial, like
Exactly.
the beginning
Someone
to
has
it.
to hit.
Right. Okay. But then every, like, say there is like a one runtime or one procedure calls another procedure, that's no longer
but
extrinsics.
This can happen. For example,
Okay.
imagine one case, I send I don't know, I send a transaction, right? So the first thing I send, I mean, a balances transfer. So I send money. So the first thing is like transfer that money, if I have it, from A to B. But then other things can happen, chain to this. For example, if I fall below the existential deposit, my account will get killed. That is like chain reaction, let's say. But it's always intra-block. So it's always in the same block, right? So essentially, I cannot chain. Because what we told, right? That
It's extrinsic.
yeah, exactly. As users, we are not allowed to essentially schedule interactions.
Okay, thank you.
Yep.
Follow-up question to that as well. Is it similar? Is it still extrinsic? If it's a gasless transaction, or if you do like gasless fees?
I'm sorry. Can you repeat?
I know there's some features in some blockchains that have gasless fees. Like you just do bulk upfront payments to get gasless transactions. Is it still an extrinsic, or is it?
If you are talking something like account abstraction or
Yeah.
okay,
Yeah.
if you are referring to account abstraction, which is ERC 4337, right, in Ethereum, and other blockchains have them as well. Polkadot, because of this idea of being fully generic, Polkadot SDK, I refer, so substrate, there are no gas-free transactions, but there could be. You could build a pallet that, so someone in the other room could build a pallet. Actually, it's one of their assignments.
Yeah.
So
it's kind of
they can build a pallet to take transactions in that pallet, actually in a bit different way. It's with an extrinsic, but with an unsigned extrinsic, actually. But anyways, so they can take transactions, process them as usual, and make someone else pay the fee, right? So this can be done in a pallet because Polkadot SDK is so generic. It allows you to essentially any kind of logic build it on top of it, right? But as I say, in Polkadot, this Polkadot mainnet, let's say, this pallet does not exist. So there are no gas-free transactions, but there could. Actually, in the future, with this extrinsic V5, this makes it even easier to, and we will explain this afternoon.
cool. Thanks.
Is there a limit in the amount of extrinsics that can be run within a block?
Actually, yes. So the limit is 256, but there is a limit of weight. It's like in Ethereum, right? There is a limitation on how much gas you can process in one block. But there's also a hard limitation of 256 extrinsics. There was a bug recently that basically would allow anyone to crash Polkadot mainnet. So everyone was permission to crash Polkadot mainnet essentially. They discovered the bug. They would stall the chain. Essentially, the bug was, we will send them a link because it's very interesting to read. Or if someone wants to look for it and send it. Thank you. And essentially, what was happening is that you could submit a transaction that the block producer could put it in a block. The block was properly created, but when trying to be imported by other entities, the block crashed the other node. So essentially, it would stall the chain because the ones that created the block are continuing, but the others cannot import it, and essentially it would crash. But yeah, this was discovered, and well, essentially one chain crashed, and they said why, and then they fixed it for the other. So yeah, there's a hard limitation.
And everything in a 6-second time frame, for example.
Yeah, more or less. So in 6 seconds, it's everything. So in 6 seconds, you need to get the previous block. You need to execute the transactions, both the ones that are from the chain itself. So all the things like, I don't know, updating the block hash there, updating the storage root or whatever, all of that is it's not an extrinsic. Then executing all transactions, and then you need like to finalize the block, sign it, and send it to your peers, all in 6 seconds. So Actually, the execution time for a block is, I'm not fully sure, but it's between 2 and 3 seconds. And they want to, so they are trying essentially to reduce all the other work, the rest of 3 seconds. They are trying to reduce it as much as possible so that we have more block time execution. Anyone else? And again, take it with a pinch of salt because it's not my field of expertise. Anyone else? No? Okay, let's continue. Then, extrinsics. Okay, so we have type and versioning. Okay, what does this mean? Okay, every extrinsic, it starts with a version by, telling us essentially if it's extrinsic before or extrinsic b5, or even there were versions before, but they are super old. I mean, since I joined Polkadot, extrinsic before was the only one available, so imagine. Okay, and there are two kinds of extrinsics actually. Don't look at this yet. Let's focus on extrinsic before first. There are unsigned extrinsics, so extrinsics that we send, but without saying who we are. So there are extrinsics that are permissionless, let's say. One example of that Victor said, actually the only example of that, well, no, now there is a new one, but the one of the two examples of that is updating the runtime. So what we said is that when there is a new runtime and they post a referendum to vote, like we want this runtime or not, essentially what they do is to allow an update for a hash of a runtime, essentially. So if anyone after the referendum passed pushes to the chain a runtime that the hash of it is what we allow, then we authorize the runtime upgrade. And this is one unsigned extrinsic. So anyone permissionless can push an extrinsic without signature, without saying who they are, saying I am providing the runtime that you already authorized. This is one example. And the other one, taking a bit what I forgot your name, Watson. So taking what Watson said, in order to make gas-free accounts with extrinsic before, we have to use unsigned extrinsics that are processed by the network as if they were from no one, but actually inside of the call, inside of all the parameters of the transaction, we say who we are and a signature and all that stuff. And this is used for pallet revive. So essentially now in Polkadot, you can push a regular Ethereum transaction, right? Signed as if it was fully Ethereum with the gas fee limit and all that stuff, right? And Polkadot would process that as if it was an Ethereum transaction. They convert it inside the runtime to a normal transaction, and they execute it. And this is the way Polkadot found to execute essentially smart contracts as you would do in EVM chains. So these are examples of the unsigned extrinsics. There are others that we are going to see right now. If we go to the Explorer, the big small, let's go to any block. For example, this one. 166. Let's go for it. We have this timestamp set. So now, okay, you see that compared to this one that is a sign extrinsic, it says signer. It's this guy. This one, it's timestamp set, and it says there's no signer here, right? So no one signed this transaction, but someone, actually the block producer, said, okay, now in the moment of the production of the block, it's this time, right? That if you go to, so it's the UTC time, typical standard thing. And this kind of extrinsic that are found on every block, for example, if we go to the children, we still find timestamp set and parent and enter. We go to the children, we find it. So they are called inherents. So are extrinsics that are compulsory to be generated by the block author, because we need to tell the runtime what time is it. Because there are some things that are done when a time is due. For example, setting the validator set. You know that the validator set resets every 4 or 6 hours, every 24 hours. Yeah, validator set resets every 24 hours. So when the runtime realizes the time has passed and 24 hours passed already, we can update the validator set. And you could argue, but if we know that the block time is 6 seconds, why can we use? Why can't we use? I don't know when 2400, whatever. But any number of blocks passed, so that multiplied by 6 seconds, it's what we are looking for, right? You could argue that. But we cannot, because the block production is not deterministic. So we don't know exactly when the block will be produced. We know that it's at least 6 seconds after the previous one. So there's always a small delay, and that way when we when we think, okay, 24 hours, we are expected to have, I don't know, let's say 100 blocks. We always see that there are 98 or 99 because all of these delays keep piling, and in the end, we miss 2 blocks. This is it is not as crazy as in Bitcoin, for example, that one block gets produced like 20 minutes, then the next one 6, then the next one in 1 hour, no one is able to mine a block. This is not like, it's not here. It's always 6.01 seconds, you know, but this small delay keep piling, and that's why we have this compulsory extrinsic saying now it's the time it is. Make sense? Yes?
Does any block has this timestamp, or there are any some kind of blocks doesn't that it's optional?
No. It depends on the network, right? So actually, there is a runtime API that it's block builder inherent extrinsics that essentially you see that it takes text or hex, 8 bytes, and it takes a hex, text or hex. So actually, every chain has its own inherent extrinsic runtime API that generates the proper extrinsics. And then there is another runtime API, but it's okay. This crash, we need to fix it. Right? Check block builder, check inherent. You see, you can provide the block and you can provide the data, both inherents, and the runtime checks if all the inherents are there. So when a different node imports a block from a block producer, it executes this runtime API to check if all the inherents necessary for that chain were produced and appended. Does that make sense? So, for example, in Polkadot, these are the 2 inherents that are appended: timestamp set and para inherent enter, which is essentially importing the blocks from the parachains. But in another chain could be timestamp set and, I don't know, give one dot to
So
the
like
money,
on a relay chain, these kind of functions could exist, right? But on other parachain, they might not.
I'm sorry?
So on the relay chain, for example, Polkadot relay chain, this extrinsic system set exists.
Yeah.
And on some other parachain, I don't know, for example, People's Collective or
Exactly.
might
In
not.
this case, timestamp set is almost always there.
Ah.
At least I didn't find a chain that doesn't have it. But yeah, they could vary. For example, I think if I'm not mistaken, they have a different para inherent in this chain. A different inherent, sorry. Yeah, this is a parachain, and therefore there is timestamp set as usual. But for parachains, there is this set validation data, which is a different extrinsic, right, than the one we had before, which actually is doing the reverse thing. In the relay chain, we are importing the blocks from all the parachains, and on every parachain, we are importing the latest known finalized block, essentially. So the block we are building on top in that parachain. Does that make sense? So essentially, it depends on the implementation of the runtime.
Just to confirm, timestamp is UTC.
I'm sorry?
Timestamp is at UTC.
Exactly. Yeah, yeah. Timestamp is the. So
Okay, yeah, no, okay, see that.
if we do new date, blah, 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 this blog was produced on Sunday, August 31st, it's today, at 12:19:24 Central Indonesia time, whatever now, essentially. Anyone else? Okay. So let me, yeah, let's take a break because the next slide is too long. Well, not let's take a break. Now it's the time of lunch, as Matteo Renzi used to say. So yeah, let's continue afterwards with how is essentially the metadata of the extrinsic. Okay, so taking back where we stopped before having lunch, we were talking about extrinsic before, and that there are two types of extrinsics: unsigned and signed. The unsigned them, as the name indicates, includes no signature, and the signed one include a signature. Okay, but then we have these extrinsic B5, which are a bit different, okay? First of all, we have the bear, which they simply change the name of unsigned to bear. And why did they change the name? Because unsigned extrinsic does not fully cover all the cases where these extrinsics are useful. Because some of them, as I mentioned, the example on the EVM, there is an extrinsic on the Revive palette. So essentially the palette that wraps up all the Solidity contracts and all that stuff in Polkadot. That accepts an extrinsic, which is unsigned, which you have to submit unsigned. And inside that, you submit an Ethereum transaction, which an Ethereum transaction includes a signature, a different signature than the one that we use, but still a signature. So that's why they changed the name to bear, because bear means, in a way, like naked, right? So it's only the transaction, and that's why they changed the name. And then we have general, which I'm not going to deep dive into it now, but essentially it expands the possibilities of extrinsics, and we will talk about that at the end of the lesson. Well, first question, I'm explaining myself very bad.
I mean, the version 4 and 5, does the version 5 switches the unsigned and signed, or they exist together?
Good question. Yeah, definitely I'm explaining myself very bad. I didn't mention this. These are two groups of extrinsic. So essentially, one blockchain, the Polkadot blockchain, could exist only with extrinsic B4, only with extrinsic B5, or supporting both. The thing is that we see that from B4 and B5, bear and unsigned they go together, let's say. But for signed in general, actually the signed was removed in extrinsic B5. So there is this new version, which is general. We will talk about that later, that essentially allows you to introduce new ways of authorizing so basically identifying yourself rather than a regular signature. And that's why this is, we can see that in the version byte. You remember from that day, like the 8 bits in 1 byte. When we talk about an unsigned or bare extrinsic, we have all these first bits 0, and then here we encode the version directly. So this is 4 in binary, this is 5 in binary. And always these 4 bytes here indicate the version, 4 bits, sorry. But if you see here, the leftmost ones, so the ones that, the most significant ones, if we found the first two to be 0, it's unsigned or bare. If we find the first one to be 1, it's signed. You see that this option is not here in an extrinsic B5. But in extrinsic B5, we have this other option that the first one is 0, but the second one is 1. Okay? In the first draft of extrinsic B5, this was not the case. So they actually allowed signed as an option for extrinsic v5. So essentially having this first bit set, all the rest zeros, and version 5. Okay. Let me show that because it's interesting. Good question, actually. What? Oh, shit. Okay. There is this repo, which is the RFC, request for comments, in the Polkadot Fellows, Polkadot Fellows / RFCs, where when they do this kind of big changes, when the fellowship or anyone wants to do a big change, essentially you have to open a pull request or an issue to essentially ask the community, the technical community, what do they think about this change. And extrinsic, actually there is one open. So extrinsic v5 is being used and it's not even yet specified. So what are we using? I have no idea. If you look for the specification on extrinsic v4, good luck. If you find it, you send it to me, please. Yeah, it's this one. And essentially they specified initial extrinsic RFC, links and formatting, blah, blah, blah. And as you can see, I am the only one that cares about extrinsics, it seems, so yeah, you always start this way with PRs, right? Yeah, nice starting point, blah, blah, blah. So essentially a lot of comments that no one took into account, essentially. This is from October 2024, so it's like over a half a year ago. Essentially, no one took into account the comments, and another guy from Parity, this is one like team leader of Parity or whatever. Seems like looks good, and yeah, this essentially can be done. And it seems that the only people that care about that, it's us doing things, support for extrinsic v5, RFC adaptation to metadata, blah, blah, blah. So as you can see, technically, there has to be a specification. And here it's explained in the specification, if this ever gets merged, and I hope it will. Yeah, specification, because this is full of implementation details in Rust. Essentially, most of my comments there are, please, can you delete all this Rust code and explain it with, I don't know, pseudocode or whatever. So don't talk about traits, don't talk about enums. This is not like that in all comments, but there is a nice sentence. So this one is nice. I mean, it says, yeah, my Catalan is starting to kick in. It says, RFC 84 introduced the specification of general transactions. Let's go and see RFC 84. What do they say? General transactions, blah, blah, blah. Here it says, okay, 00 will be unsigned, which we already discovered. 10 will be signed, so they didn't remove actually this option. And 01 will be reserved because it will become the general transactions. And 11 is reserved for future use. So actually they didn't remove it in this one. But in RFC 124, which is this one, introduce the specification of general transactions, a new type of extrinsic besides the signed and unsigned variants. And let's see if I can find here. Changes to the extrinsic authorization. The introduction of general allows the authorization of any origins, what we said, essentially it expands the options to authorize yourself. And therefore, it can replicate the present day signed transactions. That's why they remove, for example, first implementation detail. For example, a random example, right? From Polkadot SDK and in Rust, so whatever. So that's why they removed therefore, a signed extrinsic variant is redundant to a general one, which I definitely agree, and I agreed on removing this one. Because if you can make something to be general and essentially, with one variant, you can already achieve the goal, you don't need to have it multiple times, right? So that was a good question, actually. I don't know if you specifically asked that, but I went down the path. So yeah, sign extrinsics are removed in extrinsic B5. But we will talk a bit about extrinsic B5 because I saw a lot of people asking about account abstraction, ERC 4337, and this is what it enables that on Polkadot. Okay, so the metadata of the extrinsic. It's this guy. So let me open my notes. Yeah. Essentially, first of all, this, by the way, this changed in extrinsic in metadata v16. So this is the new metadata v16 version. So that's why you might find some different things in if you check a network that is using metadata v15. Quick disclaimer. First of all, the version. So which extrinsic version do we have to use for this change? And this is a vector. This is a change from last metadata because it, as I said, one chain can support both extrinsic B4 and extrinsic B5. That's why we need a vector. Then we have the address type. So essentially, you remember all that account ID 32. So essentially, this points to the address. So this is the way we represent signed origins in Polkadot. Then the call type, remember, this is basically the transaction. So this is the call, this is the type that goes to the big enums where we choose balances. And inside balances, transfer. Type of transfer, we build the call. It's this one. Then we have the signature type, which explains us which are the options, which are the signature options in the chain we are working with. And we stop here because we will check about extensions later. We will now go to the, I will say tomorrow, the PAPI console to see what's going on. Let's refresh because Victor introduced a super nice new change. Now we have accounts. Oh, this page was not available before because some people asked like, hey, how can I add an account without going through the extrinsic? And now we can. Basically, you can select and deselect, and so it's cool, right? But let's go to the metadata that now moved here. Oh, massive. What do you see better? Dark is better? I see so light is better? Dark, yeah, I see some people is sleeping here. Sounds cool. No, but last time that we did the program, we had the projector, so not a LED screen, and light was clearly better. So yeah, let's go to the metadata. Now it's here. Let's go to the extrinsic. Let's change to Western. Okay. Now we see that versions, this Western supports version 4 and 5. Nice. We see that the call type is ID 106, that if we check inside, it's a variant, essentially with all the palettes that have runtime, like extrinsics. System, for example, right? So system, I can do a system remark. Yeah, inside here with the same transaction we've been doing all day. Then we have the signature, that what is it in Western? So in Western, we can sign with 3 different schemas. First of all, ED 25519. So ED DSA signatures over the Edwards curve, a regular thing nowadays. It's the thing that is used in SSH, in modern SSH, and all that stuff. So this is the best one. Then the second one, which is an idea that someone had in the early days of Polkadot, which you can erase from your mind. Actually, you will be using it because if you create an account directly on Polkadot.js, it will create this one. But this one has one problem. It's the same problem we've been saying all day, which is the main problem with Polkadot. I said it like maybe 70 times. The lack of a specification. If you try to look for a specification like ED 25519 or ECDSA have, it simply does not exist. So there are things that are implementation dependent, and essentially everyone copies what was done in Rust in order to create their own implementations, but actually it's not fully in a fully right way written on paper. And then we have EC DSA, which is the signature schema used in Ethereum, right? It's this is the typical one with the 2 points, right? That the public key is the reflection. It comes to me like in the how does it say? Like the well, whatever. These 2 points X, Y, that the public key is what you have down, essentially. And it's the one used in Ethereum, and in Polkadot you can use it as well, but it's not as used as it is in as the other 2 ones. But there is one thing, and there are some chains that only support this 3rd one because they are like Ethereum-like chains inside Polkadot. Like Moonbeam, for example, that someone mentioned at some point, I don't remember who that was, they only support this one. In order to support the same public key you use in Ethereum, you can use it in Polkadot as well. Okay, these are the 3 signatures we can use. And then the address, which it's a multi-address, so it's an enum. An address can be multiple things in Polkadot. It's not necessary that we only use one schema, but most of the time you will be using ID, which is this account ID 32 that we've been talking all day, essentially the regular addresses. But yeah, others are possible. Index, this one is not used. If we let's check this type, because it's a good representation as well on the implementation details of Rust coming out. This type index is a compact. Okay, inside the compact, what are we expected to find? An integer, right? Compact only encodes integers. So is this an integer? Actually, it's not. It's a tuple that it's empty. So it's a compact of something that is empty. How do you encode that? So it's written nowhere, but we encode that as actually void. So actually an empty tuple. So the compact thing, why is that? It is because in the kind of this, you remember that all palettes are this way, like super general, and you can put all your generics there and all that stuff, but they still left this compact encoding. So even if you say it's empty, it keeps the compact encoding. Then we have raw, it's not being used. We have address 32, it's not being used. And we have address 20, that is the typical address of Ethereum, of EVM chains, the typical 20 bits, 20 bytes, sorry, of 0x, blah, 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 right? What you would use in Ethereum. Okie dokie. What else? Yeah, I think that's mostly it. And now, let me jump a bit. Yeah, we will proceed with sign extensions, yeah. Then, what are sign extensions? You see that here, we have them, sign extensions and a big list. So what are actually them? We introduced this a bit in the first module, if I'm not mistaken. And probably in module 2, you talked about this, maybe, I'm not sure. But essentially, sign extensions are piece of logic. So essentially, a part of the data that you have to send to the network in order to execute a transaction that is agnostic to the transaction itself. So it doesn't matter if it's a system remark, a balance transfer, a staking bond, or a, I don't know, whatever, vote, right? It's appended to each transaction because the information inside it does not really matter. So it does not take into account what is there, right? Which is the call, I mean. So for example, one thing would be the tip, right? The tip is the typical thing. I want to tell the network, yeah, with this transaction, since the network is super busy, I want this transaction to go through very fast. So I basically say I want to pay this tip. Well, quick mark in Polkadot, this never happens because the blocks are not full. But anyways, if the blocks were full and the network were to be busy, you could use the tip to basically put your transaction before others. Then you have the Genesis hash. You remember that Sean explained this, that I think it was Sean. Basically, we say this transaction belongs to this network. So I'm signing this transaction only for a network Polkadot, or only for network people, or only for Western. Then we have the nonce. You remember that we said that in order to avoid attacks by replay attacks, we use these nonce. Okay? Does this make sense? And then we have the mortality, right? So when I sign a transaction, I say, yeah, I want to pass this transaction, but I only want this transaction to be included in a block. So I only want this transaction to be valid if it's included before block 3496, for example. And essentially, this is it's not exactly the way it works. Essentially, what the way it works is that you say I want it to be valid for the next 64 blocks, or for the next, but anyways, that's the idea. Does this make sense? So you see that here, we can already see that there are some things that are kind of obvious or compulsory, or if you wish that it does not require a user input, like the Genesis hash. It is what it is. So the chain, Polkadot Genesis hash is 0x91, blah, 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 right? And it is what it is. But then the tip is actually the same transaction could be valid with tip 1 and tip 2000, right? Both are valid. This is why there are actually two types of sign extensions. Now, the first part of the sign extension is the implicit part. You will see as well that because this name changed recently in the metadata v16, as I have been saying all day. Before it was called additional sign. So if you find anywhere else mentioned to additional sign, it's the same as implicit, has the same meaning. The thing is that some of this information is implicit, so it doesn't need to be there. So the chain already knows it. So if a chain receives a transaction, it does not need to receive as well the Genesis hash, because it already knows which is its Genesis hash. The same for the spec version. When you sign a transaction, you say, I want this transaction to be valid only in version 35 of the runtime, right? So to avoid runtime upgrades that then essentially break your transaction. So you were supposed to be doing one thing, but with the runtime upgrade, the thing changed. So that's why it exists. And the thing is that, imagine that if every transaction on the blockchain in Polkadot would include this Genesis hash, every transaction would be 32 bytes longer, right? Because if a transaction takes, I don't know, 100 bytes, you have to include the Genesis hash is 132, and this multiplied by 1 million or 1 billion transaction, whatever we are trying to hit in Polkadot, this is, I don't know, maybe 1 gig of already 1 gig of block space, right? We don't want to spend that. That's why they are signed. So when we will see there, we will see an example of that. But when you sign the transaction, you are actually signing this information, like the Genesis hash or the spec version and all of that. But when you send it to the network, you don't include it, so that the network, the runtime itself, introduces that data back in order to verify your signature. We will see an example right after. But then there are others that need to be explicit, so that we need to say that actually this, which is what do we want, right? These are called extra in the Polkadot jargon. But for example, the most obvious one is the tip, right? So I actually need to include in the transaction, which is the tip, like, I don't know, 30 DOT. I want to pay 30 DOT for my transaction. The mortality is also very obvious. I want my transaction to be valid for 64 blocks or for 128 blocks or whatever. Essentially, the sign extensions that can accept more than one valid value, they need to be this way. And if there are the ones that can only accept one valid value, so the Genesis hash, one and only one, spec version, one and only one, the one that is current at that moment, those can be implicit. And then I say nonce, not really, right? Because how many nonce values are valid in in one point in time? Yeah, Kyle?
The one after that's found on the chain already, right?
Exactly. Well, actually, the one that is found on chain, because it counts the number of transactions, and we start by 0. But yeah, exactly, only one, the one that is valid on chain. It's the only one that can be included into a block. And then why do we have to put it as an extra? We could be implicit. Anyone has an idea on why it has to be included here? So I already teased you that it is added to the transaction. So it's one of these parts that are explicit. Why is that? Why are we not saving those bytes on every transaction? Giuseppe has an idea, but anyone that it's not Giuseppe has things. Why is that? Why is that?
Maybe because if there's a fork in the chain and the block that we are pulling data from, that is not the finalized block.
Yeah.
And that's why we have a nonce on every block, so that we are putting it there.
That's one of the reasons, good one. But the main one, and the one that it's most clear to me, is that maybe I want to send to the blockchain multiple transactions, so that all of the transactions get included into the same block, right? So if you verify the transaction against the latest finalized block, maybe the second transaction will say it's a future transaction, so it's not yet valid. It does not say it's fully invalid. It's futurely valid. Remember that Sean explained that. So maybe if I want to send a remark and a balances transfer, the remark I send it with nonce 0, the next one I send it with nonce 1, and both of them can get included into the same block with one or even different blocks. Yeah, but the thing is that if we would, you want to add something? The thing is that if we compare both transactions, if we verify both transactions against one block, one would be valid and the other one would not be valid, right? Because it's future. But that's why we include it. Because we can post essentially transactions to the transaction pool that are futurely valid.
Yeah, there was a question in the Discord as well.
Yep.
Shall I read it to you?
Yeah, why not?
Yeah, sure. It says there's a possibility that the spec version might not be breaking our transaction. In those cases, is there a possibility to override the implicits?
No. So if the spec version changes, your transaction becomes invalid automatically, because we don't have a way to actually say, oh yeah, but in the runtime, we don't have a way to say, oh yeah, but this transaction actually it is valid on the next spec version. We don't have a way to say that. So if there is a runtime upgrade that changes the spec version, your transaction becomes invalid automatically. Does that make sense? The differentiation between implicit and explicit and extra? Yeah. Okay. And we see the actual payload of the extrinsic. This is the actual payload of the extrinsic. And as you can see, this call is what we said before, right? System, remark, and all the arguments. But let's focus on the first part. First of all, we have the version byte. Remember, it's that byte that says it's version 4 or version 5, and if it's signed or it's general or it's bare or whatever, right? Then we have these 3 elements that are only for sign extrinsics. So only if we sign, it makes sense, right? Only if we sign the extrinsic, we provide the origin. So we say, we are this address. We provide the signature that we will see in the next slide, which is the actual payload that we sign. And we have the extra. So the part that we said, the explicit part of the sign extension. And then we have the call, which is the regular transaction by itself. Does that make sense? And these 3 parts are only for sign extrinsics. So shape for an unsigned extrinsic is just the version byte saying it's version 4 or 5, and it's not signed, it's bare, and just the call. And coming back to the module 1, it is opaque encoded. So when we send it to the blockchain, we don't send it directly this way, but rather doing what Sean called a double encoding, right? Taking these as bytes and encoding them as if it was a vector of bytes, right? So first of all, we put the length, prepended by its compact encoded length. Make sense? Okay, and yeah, that's it. But now what we have left, it's the sign payload. So as you can see, there are some parts of the sign extensions that we don't include here, but we still want to make sure they are part of our transaction in an indirect way. And therefore, the signature is generated by calling the sign method of whichever schema you're using, ED25519, for example, with the call data, so system, remark, with these arguments, then the extra part, so the part that is explicit of the transaction, and then the additionally signed or implicit part. So actually, when we are signing, we are including this spec version, Genesis hash, transaction version as well, there is one, the check metadata hash that we talked the other day. So all of this is being included here. Yes? And then the node, in order, actually the runtime, in order to verify the transaction, needs to rebuild all of this, right? So take the call from the extrinsic we inputted, it takes the call, it takes the extra, and it rebuilds the additionally signed with the only valid values that the runtime has, and it checks that the signature is valid for that input and this origin. Make sense a bit? It's a bit going in a lot of places, but does that make sense? So basically, the call in the extra we provided to the node, to the runtime, sorry, and the additional sign is generated by the runtime at the moment of signature verification. And then it has to match, the signature has to match the one that we provided. Yeah? More or less? Questions? No? Okay. Yeah, let's see examples. And this, I'm going to do it with, I have to reshare my screen. We're going to be doing a bit of a live coding. We are going to use a library. Well, first of all, we are going to use the main client of Polkadot, the one that Polkadot API, the one that you are using. And we will be using as well a library that we develop as well, that it's outside of our main client, which is called txutils, which allow us to essentially decode this kind of extrinsics and all that stuff. Let's go for it. Zoom in. See, good zoom back there. Yep. Yeah, all good. Okay, we are missing to install the add txutils. Okay. And then let's see which Genesis and Polkadot. Okay, perfect. Then let's create the client. Make it a bit smaller because otherwise I don't see. But yeah, we create the client as usual. We give the, sorry, I'm using my voice. Okay, we create the client with the type API and all of that. And now let's create our txutils, extrinsic decoder. Import from txutils, get extrinsic decoder. Okay. what does the extrinsic decoder need? Const decoder. It needs the metadata. Where do we find the metadata? Do you remember? We talked about this morning. Where is the metadata stored? Anyone remembers? No one? Where do I have to go in here to get my metadata? If someone can guide me, we did it this morning. Is the metadata, we get the metadata through an extrinsic, through a transaction? Not really, right? Because to build a transaction, we need the metadata. Storage, okay, you guide me. Which is the palette in which the metadata is inside? Metadata is a? It's a runtime API, actually. We cannot use storage without the metadata because we don't know which shape it has. So there is one runtime API, which was called metadata. Remember that we did this morning? This was a runtime API. This is a node API. We know what it will return, even though we still don't have the metadata. The metadata could be self-descriptive, but we still need a way to decode it, right? So, okay, let's use, if we call metadata version 15, it returns me the metadata. Amazing. So I'm going to use that const metadata. It will be, let's await, API dot, we said it's a runtime API, right? So inside APIs, we said it's metadata, and inside metadata, we want the version 15, for example. Metadata at version 15. Okay, what does this return? This could be a binary or undefined. We know this is not undefined because we know that metadata version 15 is present in this chain. So I will add this assertion, but technically you could check. Is it undefined? I throw. It is not. Okay. And this returns a binary, but this is not exactly the type our extrinsic decoder wants the metadata, right? It wants a uint array. The binary is our abstraction of a byte array. So actually, if we want the bytes, we can just call as bytes, okay, and get it. Make sense? Yes. Okay, so now we already have our extrinsic decoder, which we can call decoder, and pass here a value, uint array, or a buffer, string, so anything that it can understand. And it will provide me a decoded extrinsic. Decoded extrinsic. What is a decoded extrinsic? Let's figure out the type. What's going on? What? Well, let's go manually. My TypeScript is going mad. So the decoded extrinsic will return this. It will return the length of the extrinsic, okay? It will return the call data, which, if you remember, it is always present, right? It doesn't matter if it's signed or unsigned. So it will always be here. And then the version can be 4 or 5, and it can be of type bare or unsigned, which is the same. And then it can be, if it's version 4, it can be signed, and then it would include the address, the signature, and the extra, which are these 3 parts. And if it's of version 5, we didn't talk about this yet. So let's get some extrinsics. Let's go to the console so we get a block that it's interesting. Until here, everything that I did, like creating the client, getting the metadata, all of this should be fairly understandable. I think it's this one that was working for us. This bug will be fixed at some point. we will take care of it. Oh, shit. Let's use small dot. Let's see if we are more lucky. Yeah, we are more lucky. Let's wait until it loads. Okay, it already loaded all the events. 344 seems interesting. Okay, we have 3 extrinsics in this event. We have timestamp set, typical one we want to find or we expect to find. We have par inherent enter and utility force batch. Okay, this force batch, we didn't see it yet, so let's see what it is. Let's copy the block hash because we will use this extrinsic as we will use the extrinsics of this block as an example. So do you know how to get the body with Polkadot API? You have it fairly easy. So body, it's in the client, you have an option to get block body, and you have it as well as an observable, if you prefer that way. We will get the body of this hash. We will have no problems because we're using a socket provider. And this, what is it? This is an array. The body of, in any blockchain, the body of a block, it's an array of transactions. So we expect here to find 3 transactions. Let's see if we are actually right. And body, let's console log body.length. Let's see if actually we find 3 transactions and it works out. We said this node was yeah, it's not down. Okay, yeah, actually 3 transactions, perfect. We are in the correct block. Nice. And now let's use our decoder to decode the first one. Let's see what we find. Well, first of all, let's see the look of it. So let's do console log body, the first transaction. And let's do that for all of them. No, let's not do the second one, otherwise it will be too big, the output. Okay, these are our 2 extrinsics. First of all, we find 0x28. What is this? What we said that we find on every extrinsic before. It's so the first bytes. You remember that we said that it's opaque encoded, right? So the first thing that we receive is the length of the rest of the extrinsic. So 0x28 actually means 7. So technically it means 7. Yeah, I think it means 7. So technically we have 7 bytes after this one. Okay, let's suppose it makes sense. What does it say here? What is the first thing we find in an extrinsic? The version. Which version is this? 5. And is it signed? Or in this case, it's version 5. So it can be general or bare or unsigned. Let's see. Is it signed or is it not? Let's check our documentation. It says if you find the byte to be 5, so with these bits, it's going to be bare. And if you find 69, which is actually with this bit set, it's going to be general. In our case, it was actually unsigned, right? And what is this? This is actually the timestamp set, okay? Then we will decode it and see that actually it's the timestamp set. And then let's see the second one. This is this utility force batch. Do you remember? Okay, let's see what's going on. This is the length. Okay, this is the length. Believe me, this is compact encoded. So, but we really don't care about the length. It's opaque encoded, so we understand the extrinsic. And this byte would be the version 1. So that the one for the version. Which version does it have? This one. It says 84. 84, it's version 4. Actually, for the version, we only use the rightmost speeds. And if we go to our docs, it says that if we find 132, which is 84, but in decimal, right? 84 is in hexadecimal, right? So it's in base 16. If you don't believe me, 0x84, it's number 132, okay? So they say, if we find number 132, it's actually a sign extrinsic of version 4. Okay, cool enough. And then the rest, we will need to decode it because this is too big, right? Let's decode them. We will use our decoder. Let's resize this so that you guys see. Okay, let's use our decoder. Cons, first one, decoded. Best naming ever. Coder, and we'll use body 0. So the first, what's that? Yeah, TypeScript. Because it's complaining that you didn't check this array is of length at least 1, but yeah, we checked actually. Let's resize this. And let's run. CL first. Okay. Let's see what it decodes to. Bam-ba-dam. Oh, sorry, I forgot one thing. Yeah, but let's start with the beginning. It says length is of length 10. Okay, whatever. It makes sense, right? Because it's 7 plus the bytes that we needed, whatever. Then version 5, what we already discovered, it's of type var, and then it has this call data, which this is you remember this binary is our abstraction over in data arrays. We don't care, but also we have the decoded call. It says that it's timestamp set, and the value, it's one of these binaries that we talked about. So actually, what we were looking for. And the second one decoded. Second, do this. So it brings the whole. Okay, let's see the second one. Okay, what does it say? First of all, length 145, okay. Version 7, version 4, type signed, what we already discovered just by looking at the bytes manually. And now we have the address, because since it's a sign extrinsic, we know this is the payload we are looking for. We hope to find the address, so the origin, address, origin, all the same. We hope to find the signature, and we hope to find the extra part of the sign extension. Let's see if we do. We find the address. This was the address that was able to send and sign properly this extrinsic. Then we have the signature. In this case, it was with the algorithm SR25519, and the value, again, it's a fixed size binary. We can show it as hex or as bytes in order to see its content. In the end, it's just a bunch of bytes that are the signature. And then we have the extra. Oh, and look at this transaction. First of all, we say check non-zero sender. It does not require information here. Check spec version. You remember, spec version does not require to be here, so we find it as undefined. Check TX version, same. Check genesis, same. Check mortality. These are the one that we wanted to add here. In this one, the transaction is of type immortal. So the author of the transaction is trying to say, hey, I want my transaction to be included regardless of which block are we. Not very recommended, by the way, because it can lead to repeat attacks in some corner cases. Check nonce. So the nonce is 339. This account made a lot of transactions. Check wait. This is nothing. Charge transaction payment. This is what we call the tip. It's called this way. 0n. So this transaction included no tip. And then check metadata hash disabled. This is another security feature. And in this case, this user didn't use. And then the call was a force batch. So it's essentially when you find utility batch or something batch, basically what it means is that the user took several transactions and said, I want to execute all of them at the same time, like one after the other, all on the same block. And what did this user? Staking, payout stakers. So it paid out to some stakers, requested the payment essentially, this validator stash in this era, whatever. What else? And that's it. So it did a batch of one transaction. Probably this is an automated script that essentially creates the first batch. And if there are multiple rewards to be asked, it appends all of them. It's not a very good use of resources, but anyways, it was good as an example. All of it makes sense? The most important thing you have to understand here is the difference between signed and unsigned, which is clear. If it has a signature, it's signed. If it's not, if it doesn't, it's not. But also the part of the sign extensions. It has to remain very, very clear that the sign extensions, first of all, are only included if the transaction is signed. That's why they are called sign extensions. And that there are two parts, right? The part that it's obvious to the chain and the part that is from account input, let's say. Yes? Okay, now let's proceed. I think it's extrinsic B5 now. Yes. And this extrinsic B5 will mark the end of the session. So essentially, what is extrinsic B5? What's the goal of it? It's probably more of a philosophical goal, right? But the idea is to remove the origin and the signature from the actual extrinsic. So we don't want anymore to have signatures or addresses on the extrinsic. And why is that? Because actually it's very handy, right? We say, I am this person and I'm signing with this private key, that this is its public key, and it's handy. It's the way we often think that we can do actions, even in real life, right? If you want to, open a bank account, you need to say, I am this person, right? With an ID or a passport or whatever. In blockchain, the way we have to show a passport is sign something, right? With my private key that technically only I know. I represent myself as the owner of this public key. But this is not the only way of making transactions. Or this is not the only way of saying who I am. Why is that? Because it is very strict, right? This way of thinking. Does that make sense? It's like forcing you, extrinsic before is forcing you to authorize yourself like that, with a regular signature scheme and with a regular address that it's fixed. The runtime developer cannot choose, right? The address is the address, the signature is the signature, and the palette developer cannot say, yeah, but I want my palette to authorize this way. And that's where it comes extrinsic B5. Then an example of how they overcome this rigidness, if you wish, of extrinsic before the release of extrinsic B5. And it was through unsigned transactions. So instead of leaving the authorization to the general part of the extrinsic, so the part that is for every extrinsic, right? So the part that in sign extensions or in here, oops, yeah, or in origin and signature, what they do is they use an unsigned transaction. So basically they say, okay, this transaction that I'm giving you is unsigned, and the call that I'm making, it already has a way to authorize myself. This is the example with the EVM thing. You remember that I mentioned it multiple times, that in Palette Revive, when you want to submit an Ethereum transaction to interact with a Solidity contract or something like that inside a Polkadot-based runtime, you do it this way. Actually, let's see it. Let's change to Paseo Asset Hub. If I am not mistaken, it should include what we are looking for. Okay, so waiting for metadata. Okay. If we go to extrinsics, we go to Revive. It has no Palette Revive, so it has to be Passet. Okay, Revive. You know that there's this transaction called ETH transact that actually just takes a payload, right? It takes a bunch of hex. And what does this hex mean? Let's look at the Revive palette, calls, ETH transact, and there is no documentation here. Wait a second. Revive ETH transact. Okay. It says this is the call we are trying to go with. It says ETH transact performs an Ethereum call. See, create, palette, dry run, ETH transact, blah, blah, blah. So essentially all of this 0% descriptive information, what it's telling us is that there in that payload of the extrinsic, which is just an unlimited number of bytes essentially, so a vector of UA, what it's telling us that we have to submit an Ethereum transaction. And here, this transaction will be accepted by the network if it's unsigned, because here inside, we already have the Ethereum way of authorizing, right? This is the big flexibility of Polkadot, as you can see. It allows us to authorize ourselves through a palette. So this is a palette. This is not like the core of the runtime, but rather a palette. But this has one problem, and it's that every time we want to use a palette that includes this kind of particular authorization, like the Revive one, we have to make changes to the core part of the runtime. So the part that actually authorizes the transactions and all of that. So if we look at the code of the runtime, let's see if I can find it. Relay, no, not relay, sorry. System bar chains, asset hubs, Kusama, I think it's in Kusama available. Flip, Revive. Look, here the unchecked extrinsic, so basically the type of the extrinsic itself, it's a palette Revive EVM runtime unchecked extrinsic address signature, blah, blah, blah. So it's already integrated inside the palette. So the whole network is going to be using an extrinsic that is from a specific palette. Imagine that now we want to have a different palette, I don't know, for doing account abstraction or whatever, that also needs this kind of authorization to allow for gas-free transactions. We would most likely need to update this, or at least make it more generic, so that we can do this so that we as runtime developers can use a palette that uses a different method of authorization. This is not very handy. It's actually very shitty because you always need to keep making changes to core parts of the runtime. And imagine if there is a vulnerability in the lowest end of palette revive, it could affect potentially the whole network, not only that specific palette. So that's why Extrinsic v5 comes to save us, essentially. And in order to avoid making these changes, the solution is as follows. This is the Extrinsic v5. First of all, the version, and we have the call, same, in the signed, unsigned, or bare, as they are called in Extrinsic v5. We have just the version and the call. This doesn't change. But instead of having the address, the signature, and the extra part, we only have the extra part. This is just an extension version because in Extrinsic v5, they also introduced versioning for sign extensions, but it doesn't matter for the purpose of the point I'm trying to make. We just include the extra. And why is that? Because the goal now is instead of authorizing ourselves through the hard-coded way, through saying, I am this address or I am this other address, the idea is to authorize ourselves through sign extensions. So there could be different kinds of sign extensions. For example, Ethereum, there could be a sign extension that is Ethereum authorize, for example, that I can authorize myself the same way I do in Ethereum. There can be another way that is gas-free payment or whatever. So if I use correctly this sign extension, I will be able to do a transaction. And now you can think of, but yeah, now how we build the old transactions, right? The regular account sends money, so A sends money to B. How we build them? Through sign extensions. Now there will be a sign extension that will be regular origin, if you wish, and regular signature. So if we want to authorize ourselves in the regular way, we just activate those sign extensions because most of them are optional. So we say, yeah, I want to authorize this way or this other way. This makes it, if I'm explaining myself correctly, this makes it more handy to add different kinds of authorization. And this works well with the idea that someone had here or asked me about account abstraction. So what happens with that, right? And maybe we want to add a way to authorize with these passkeys, right? That are super, everyone uses passkeys now. So technically we could build a sign extension that it's a passkey authorizer and have it here. And it would, without changing the extrinsic, we have this option now. Or, for example, I don't know, authorize ourselves with the GitHub account. Maybe that's our thing, right? We want to do this easy single sign-on in our blockchain. Maybe not in Polkadot, but if I'm building a random blockchain, maybe single sign-on, it's enough for me. So I could create an extrinsic that is single sign-on, GitHub, whatever. And now there is the actual goal of these ones is to use zero-knowledge proof. So that the idea is that you can authorize yourself. For example, if we could build a zero-knowledge proof, we could use zero-knowledge proof here so that you guys can authorize yourselves as members of the PBA dApps track, best track ever, but without revealing your actual identity. You just reveal partially your identity. You just say, I am a member of the dApps track. And then I can tell to the other guys in the other room, hey, I am able to, I don't know, do this interaction that you are not able to do because you don't have the authorization to be this one, but no one knows that the one that sent the transaction is Kyle, right? Make sense? So this is one thing that previously we cannot do. And now, since sign extensions are basically code, we can code whatever you want, whatever we want inside of the runtime. But this also comes with challenges. So not everything is free and, not everything is easy. Before it was super clear who was the sender of a transaction, right? I go to the extrinsic. If it's unsigned, of course, there is no sender. But if it's signed, it's clear. The signer or the sender of the transaction, it's this guy. No one else but this guy. Now, who is the signer of the transaction? I actually don't know. I could potentially go and check all the sign extensions, or at least all the ones that I, as an off-chain developer, know, check which ones are enabled. Maybe the Ethereum one, I can handle it. Check it as if it's an Ethereum signature. But maybe this, the zero knowledge proof, I'm not capable of doing it. And this is the main challenge that extrinsic V5 gives to the network. But technically, runtime APIs could help here, because we could have, actually, this is nowhere. So it's just an idea that I don't know I had, but there could be a runtime API similar to the, you remember the one like the view function we showed, like check permissions for the proxy palette, saying, I have this proxy and I want to know if I can execute this call, right? So similar to that, we could send an extrinsic to the runtime through a runtime API or view function and ask, who is the author of this transaction? Who is the origin of this transaction? And potentially the runtime API could send me back saying, this transaction is authorized through this palette. And maybe this palette provides a way to say, yeah, it's authorized through blah, blah, blah. So potentially we could have some more of these interactions with the runtime, so that even though we don't know from outside, we can ask the runtime who is the actual sender. Okay, I talked for 20 minutes straight. And the thing is that there is a comment here in blue, which is what I wanted to highlight now. And it says, it's a really good idea to add PAPI to the post-install script in package.json to automate generating the types after installation. What does this mean? What it means, make this big, test, our test. What it means is that, you know that scripts, you know that in the package.json you have this scripts option, which basically you can set build, you can set run, you can set whatever you want. So there is one that it's post-install that actually, well, the JSON language server protocol already tells us it's run after the package is installed. So actually what you can do here is do PAPI. Then when you do ban add, I don't know, imagine that I want to install noble hashes, whatever. After this, it executes PAPI automatically. So it ensures that PAPI is executed every time you change anything, or even if I remove my node modules and I do ban install, it executes PAPI. So if you add this to the post install, then you will not forget, essentially. So yeah, that was one thing that I wanted to mention. Okie dokie. It's in the docs, but yeah, it's going here as a quick comment because it's only relevant to some kinds of installations. But in this case, this is one, like dApp is a perfect use case for having this post install. Then the other thing that we didn't talk about is this guy with Polkadot SDK compat. Basically, we said, put it there and everything will work magically, but I know you guys you don't have enough with that and you want to know why. So let's go to the documentation again and see why. In the requirements, it says, PAPI is designed to work flawlessly with almost any Polkadot-like chain, even though we have some requirements that the chain and environment have to fulfill. The person that wrote this must, yeah, it has to be super intelligent, super smart. Well, Node.js, whatever, recommended 22x. It says ban. You can use ban to run PAPI code. And there's a comment here. In case you are using ban, then PAPI will work flawlessly with it. But just a small detail. If you use a WebSocket provider with ban, you can use the web version of it instead of the Node version, because ban already includes the modern WebSocket, let's say, the real WebSocket. And if you're using Node 2022, so this latest version, you can also use the web version. So this was another thing. And why is that? So essentially, it's because of this. If using Polkadot API through Small.dot, there are no specific requirements. So basically, PAPI and Small.dot understand each other and everything works. So we don't need any compat or whatever. But when using a WebSocket provider, there are these three cases. Polkadot SDK, if Polkadot SDK is version is rated at 1.11, then it will work without issues. But no, it won't work without issues because a new error in Polkadot SDK has been discovered, blah, blah, blah. So what does it say if the version is old? Basically, if your versions are between 1.1 and 1.11, you don't need to know about these versions. This is more for when you build a dApp and you are from a specific parachain, basically. What it says is that the node implements the JSON RPC spec wrongly. So it does not fulfill the specification of it. It does not, essentially, they do things wrong. And we, from the library, we enhance the JSON RPC connection, well, the WebSocket connection, and we enhance the JSON RPC messages so that even if the node does not behave properly, we fix that misbehavior. And that is what with Polkadot SDK compat does. It fixes these misbehaviors. One good thing is that you can always add it, even if your version is super high, because this enhancer fixes misbehaviors. If there is no misbehavior, everything will work as expected. So that's why the recommendation when using a WebSocket provider is always having Polkadot SDK compat. Yeah? Make sense? Okay, nice. These were the two things that I think from yesterday we forgot to mention. And well, there are some runtime requirements, but essentially every chain fulfills these requirements, so you don't have to worry about that. Yeah, regarding this, honestly, I really recommend checking our documentation because even though it's not super complete and all that stuff, you have quite a bit of information. Well, in the getting started, you have essentially what we did yesterday, explaining all of this. And in the specific section for providers, we explain WebSocket 1, which is the one that is the most different. We explain this part of the switch and get status, which are specifics to the WebSocket transport layer, right? This is what I said. Remember yesterday that I said for a WebSocket provider, you can, where is it? Yeah, here, endpoints. There is an overload, which is passing an array of strings. This is, here it is explained. And also what you can do is to force a change. So say, I want to switch now. It's here. There is a switch function to say, I want to switch now because the endpoint is not working. Switch to this other endpoint. So this is all explained here. And yeah, this part is not particularly bad, so you should be able to find it. And as well, if you want to know some things about signers and how we treat signers, we will go deeply about this in the course. But if you are interested, you can check it out. As I say, it's not that bad. This section. Okay, and as well from the top level client, you have documentation for every interaction, like constants, runtime APIs, view functions, storage entries, events, and transactions, which are all the interactions we support. Well, essentially every interaction. And it's mentioned as well the unsafe API, which you don't need for this assignment. But anyways, it's here if you need anything. So I highly recommend checking the docs. Okay, now after this, let's start with the questions. Questions regarding the assignment, regarding PAPI, regarding whatever. I hope I thought everyone had a lot of questions and everyone was super lost, but I like it that. Okay, so in that case, I don't really have anything else to add. Do you have anything else that we forgot? Would you think?
Maybe I can continue on the sample template because we want to.
Okay. Yeah, good idea.
Okay. Oh, don't worry, I'll make everything bigger in a minute. I want to change to. But from there, I think. Is it working? No. Yeah, they say it's working now. Yeah, it's okay. PBA Bali getting started. There it is. Now, yeah, I'll do that later. I was working with some of the JSON RPC stuff. Okay, my idea is to continue with what we had yesterday. Well, first fix what Carla mentioned now is that in this repo I forgot to add PAPI to the post install script. So that's something I can just do here. PAPI. Now this way, when anyone clones this and does npm install, then it will just work. And the other thing is in main what we had here. Yeah, I use this get WebSocket provider without the Polkadot SDK compat. And as I don't know what AM fork has, I'm just gonna also wrap it with Polkadot SDK compat. It's this simple. Okay. Now my idea here, I will clean the exercises we had from yesterday to have it a bit more small. It is like that, and I'll commit this. Git commit, fix, install, and SDK compat. And my idea is to now see how you can create a transaction. I think that for the assignment, you don't need to create a transaction just yet. But it's still it's something that people usually, find it oh, how do you integrate with the browser and all of that. So this is a bit on top of my head, but it's not that hard. Famous last words. So get injected extensions. We have this function from Polkadot API PJS signer. And if we do this, const result is And now I need to npm dev. It might work directly or not. We will see, but it's going to be. It's not this one. Sorry, this is what I was working before, and it's still running in the background, and it's not what I want. I'm sorry about that. Now, yeah, it worked. Okay, nice. Let me make this bigger. So the way that Polkadot.js, like Polkadot extensions work, is also not based on any specification, as always. So this was essentially Polkadot.js created their own extension, which is this one. And I can also do something here to make this bigger. Displays. So whenever you install an extension, it's up there. And what Polkadot.js did is like, well, I need dApps to be able to access me in order to create transactions and sign them and so on. So what they did is just like not part of a standard, but there's an object in window called injected web3. And this injected web3 is an object that has each one of the extensions with an API that here you have like enable, and then inside we can try and call this inject web3 of Polkadot.js enable, and then it's a log in there. And then you can see that this gives you another object with all of the accounts, metadata object that in here doesn't say anything, but it has more stuff in it. But basically, like this is the API that came up with of like offline first, so like the metadata is static and you have to update it and whatnot. But essentially, from here you can assign stuff. However, Polkadot, like this is like a bit hard to find. So in PAPI, we have made an abstraction on that, which is like this get injected extensions stuff. This could be big enough. So when you do get the injected extensions, all it does is just returns a list of the keys that are inside that object. So at least you don't have to know about which object it was, but it's injected web3. You have it there. And then there's another one, which I think it's get extension or something. Connect injected extension. There it is. Which now extension connect injected extension of the first one that I can find. And now this thing I have to wait it because now it needs to create the connection. And now this returns an injected extension that has everything in it. So if I do extension dot, then I can see that I have a method to disconnect and say like, okay, I'm done with this. Like usually you would do this when the user wants to disconnect from the account, yeah? Then you have a get accounts, and this will give you all of the accounts that this extension allows you to sign with. And well, subscribe is like, because here the user can also come here and say, okay, I want you to have this one as well. So when you do this, and I say like, I also want this dApp to be able to see Charlie, I'll get like a subscription like notification so that I can update my dApp and so on. But usually, like if users want to sign, what you would do is just like get accounts, and this gives you a list of accounts. So accounts. And you can see that there are 5 accounts, and each account has their name and everything in it. And then the most important part is like this Polkadot signer. So with this Polkadot signer is what you can use in your dApp in order to sign the transactions. So let's say that I'll do set timeout because I don't want to have it like too quickly, but we'll do set timeout of 1 second. So after 1 second, I want to make a system remark. Then I can just take the type API, transaction, system, remark. And then here it's all fully typed, so you can see I need to pass in a remark, which is it's a binary, but I can just do binary from text. So now I can see, hello, PBA. So here I have my transaction essentially. And now this transaction, I can do multiple stuff with it. So like there's like a lot of like, oh, I want to know which are the fees that are going to be called. I want to know what is the weight. This is even more low level. But then we have these three methods over here, which are the ones that we're interested in. We have sign and submit, and sign, submit, and watch. So it's like three levels of things you can do. So if you sign, you will just like sign the transaction without sending it, and then you have like the signed stuff, and you can send it later, or you can, I don't know, do whatever with it. The other two are the ones that are more interesting. And the only difference is that the first one, sign and submit, will submit the transaction, and then it will wait until this transaction has been like fully committed on the finalized block before resolving the promise. So you submit the transaction of like do this transfer, and once this promise resolves, so I can do this, sorry, sign and submit, and then I need to pass a Polkadot signer. So this is where I get my accounts and say like, well, let's do account, this extension, get accounts. I'll just pick the first one. This is like in here you would like put a UI of like with what extension you want to sign and all of that. So I want to do it with the Polkadot signer of this account. And now, const result, you can see that this returns a promise of a transaction in a finalized state. So this transaction that I'm sending, it has been included in a block, and then it has become finalized, and then you have the result. What happens if the promise is invalid? I don't know how can I make an invalid transaction now. But if the promise is invalid, then you just get a promise reject, right? Like the promise could not be included in a block. But if it was included in a block, even if it failed, then you will still get that. So if I do transaction await, this thing, and I have to make this asynchronous, then you can see here that there's a property called OK, which means that if the transaction succeeded or not, essentially. And you have like all of the events and all of that. Now, if you do this, you will see that yeah, there's a question there.
Since it's a promise, if you do like a try catch block, will the exception tell you why it was invalid or why it was thrown?
That's a good question, and it will tell you. Yeah, if it was invalid on the error, you will get like I think we actually have it as an exported type exception. I think it's invalid transaction error. Yeah. So like the type of the error you get is like this one, as any. And then the exception you can see everything. So you can see like the message, the cause, and
Okay, yeah.
and the name and everything.
So it's like a typical promise structure.
Yes.
Like yeah.
The only problem is that in JavaScript errors are not typed, so you have to know it. But you would see that it's of type invalid transaction error.
Okay.
Yeah. That was a great question. Where was I? Yeah. Yeah, exactly. So on this note, like if you do sign and submit, what you will see is that you sign the transaction, and then you have to wait like 12, 13, 14 seconds until the promise resolves, which is like, what is happening? I don't know. I'm getting anxious. Like, is it going through? Is it not? So this is why we have like the transaction, sign, submit, and watch. So this is a bit more powerful, and essentially it does the same thing. So address, sorry, Polkadot signer. But now it returns an observable. So it's like this sort of like promise, but with multiple values, if you will. We have like a session that talks more about this. And then you can subscribe, and here you receive the events of like this transaction. So now it's not async await. It's a bit more hard to use because it's not synchronous and whatnot. But here you can see that you can do switch event.type. Now here we have like different stages. So the first one is the transaction was signed. So it'll do log signed. I'll do event. So you can see here we have only the transaction hash and break. Then the other one is broadcasted. So this is when the transaction has been broadcasted to the nodes and it's being passed around, but it's not yet included in any block. Like it has not been seen anywhere. Broadcasted. And here we also have the hash. Then we have, if we keep on order, it's transaction best block state. So this is when the transaction has been found and is in a best block.